Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hey everybody, I think it's about time we get started. So thanks again for making it this morning. Hopefully the rest of the stragglers will come in soon. I think maybe just one announcement. So Nate Cushman suggested we put up this sort of resources Google spreadsheet that's updatable during the course of the worksheet. That's available at the top of the website, and you may have to hit refresh a couple times to get past your dirty cached copies or something. So feel free to jump in there and add some resources. We're also going to broaden it a little bit. So if there are topics or collaborations that you'd like to bring up during that final session, like areas you think we should focus on, please just add some of those suggestions so we can address them and see how people might want to be working together either through data or resources or just in general problem spaces. Yes, Prem?
I'm just saying maybe we should just send the link out again or put it up on the slides or write it on the blackboard or something.
Yeah. Okay, I will do something.
Maybe just email it.
Yeah, I'll email it to everybody. Apologies for the spam. So with that announcement, let's get started with the first session. Thanks. I'll let Dennis and Donna take care of it.
Thank you very much. So let's get started. This is information retrieval and software engineering session, and Donna and I will chair the session. So the idea for the session, first we're going to have elevation talk for 20-30 minutes. Feel free to ask questions in between, and then we really want to push the discussion for the session. We'll have approximately 1 hour for that. So our elevation talk will be given by Andrew Marcus, who is Associate Professor of Computer Science at the University of Texas, Dallas. He has been working on information retrieval for quite a few years by now. Published many papers, graduated some students. So, and he will give us overview of the field, and hopefully it will help us to jumpstart the discussion.
Okay, thank you, Dennis. You can hear me all right? All right, since I didn't have my minute yesterday into 2 minutes to introduce myself, I go by Andy Marks. I'm Associate Professor at UT Dallas. And yes, as Dennis said, we've been using text retrieval and software engineering for over 15 years. Actually, it was a topic of my dissertation. And starting with my dissertation, and two of my students are in the room, Sonia there and Dennis, former students, and Dennis's former student, Colin, is here. So between us and two of other Dennis's students who are not here, we had actually 6 PhD dissertations in the last 15 years, all using text retrieval one way or another in software engineering. Published over 100 papers, so there's a little bit of rich history. So all of these, some of these people are here, right? You've seen Dennis, Sonia, Colin is Dennis's former student, Martin's current student, and Vina was doing a postdoc earlier with me. She's now at Washington State University. So what sort of work we have done in using text retrieval and software engineering? Well, I think over the last 15 years, we ended up addressing 12 different software engineering problems, ranging from bug localization, traceability, link recovery that we heard talk about yesterday, and Jane mentioned clone detection. Again, people mentioned clone detection yesterday, reverse engineering, not so much discussion yesterday, coupling, cohesion measurement, and refactoring, again, not a lot discussed yesterday. Defect prediction, Tao talked about it in his tutorial. Code summarization, somebody mentioned a little bit yesterday, but not much. Bug triage was talked about yesterday. Query formulation, text retrieval model configuration, and API retrievals that was discussed yesterday. So these are things we have addressed in the last 15 years, but for this talk, I don't want to talk about our work. I am going to talk about what has been done in this area. So I'm going to give a very short history of text retrieval and software engineering. I will overview the main software engineering tasks and how we address them with text retrieval. And when I say we, I mean the community at large. And I will highlight challenges. So every time you see some orange color on the slide, it's a challenge that currently, as far as I consider it, exists in the field. Okay? And some of these challenges are going to be task-specific. Some of them are cross-cutting. Right? Okay, so here's the very short history of text retrieval in software engineering. So I'm glad we have this workshop today, well, these days, and it's a lot of discussion mostly on language models, but we have been handling text in software for a long time. I wish we had a workshop like this 10 or 15 years ago. We didn't, but still we didn't work in a vacuum. So just so you know, back in the late 80s, early 90s, there was a handful of individuals, Yoel Marek, I remember, Bill Frakes, and in Somerville, who actually used text retrieval to index software libraries, and they published in the Software Use Conferences and SIG-IR. There was actually a track at SIG-IR on reuse back then. And then there was nothing for a decade, and circa 1999, and yesterday Jane alluded to it, a group of Italians started working on traceability. They still do today. It's an unsolved problem. And then 2000 is actually when I started working on it, and several other people, and we started addressing other software engineering tasks. And there was a little bit of community building happening slowly, but it was inside software engineering. I don't recall ever seeing anyone from NLP or text retrieval community. We do have some crossover. Dawn is over there. Actually, she worked on organizing some of these workshops, Naturalize, this one, right? Yeah, so back in 06, Dennis actually organized, with Dennis, we organized a working session at ICSM. That would be the software maintenance conference for those outside the field. Then there was a little bit of a gap until the field picked up critical mass. And we have several workshops in the last few years, some of them with NSF funding. Actually, one of them in particular, it's at its 5th edition this year. It's called MUD. Sonia there was the organizer this year. Actually, Dennis gave a keynote over there. So there was a community building, but as I said, to my knowledge, and correct me those of you who are in the room and know, I am aware of only 2 pairs of researchers that managed to cross-cut between text retrieval and software engineering. One of them is in the room, Dawn Lowry, who's the original text retrieval IR person, and she's working with Dave Binkley for 10 years now or more. And the other one is Vijay Shankar at Delaware, who's working with Lori Pollock, she being the software engineer, Vijay Shankar being the NLP/IR. That's pretty much it. These are the only pairings across fields that sort of stood the test of time. There were other maybe individual efforts, small ones like that, but these are the only ones. In terms of production, the field is a little bit outdated. These are papers, we tried to do a survey a few years ago, and it turned out to be too daunting of a task. That's 2012, but the trend continued like that. So in the last decade, in software engineering, actually, there have been published nearly 500 papers on using text retrieval in software engineering. It's a big field by now, right? However, since we didn't have this sort of event to be able to be introspective, that's why I'm happy what's going on here, right? Because we're sitting down asking the questions. We have language model. What can we use them? What's the best way to use them, right? We really didn't have that back in these days, right? So the community, as far as I can tell, instead took a more of a applied approach. Let's see what problems in software engineering we can solve with text retrieval. The question wasn't at that point, which is the best text retrieval model for the problem? What can we solve with text retrieval? And as it turns out, it's, by my count, 30-some different software engineering problems were and are being addressed with text retrieval today. And many people in this room are doing that, all right? So how did the community do that? Well, from what I can tell, there are 2 approaches for most, 2 ways to use text retrieval in software engineering. Option 1 is formulate the software engineering task as a text retrieval problem. And option 2 is formulate the software engineering task as a text analysis problem. And I'll explain the differences and give an example of each, and highlight the challenges that happens each time. So everybody knows what the text retrieval problem, right? You build a corpus, index it, formulate a query, retrieve the results, and go back and reformulate the query, what happens. So really, this is it. So you pick the software engineering problem, And you have to decide what you're going to build your corpus from, and how you're going to get your queries, compute similarities, and so on and so forth. What sort of tasks are addressed this way? Okay, classic one, probably two of the most researched ones would be anything related to concept, feature location, bug localizations. Those are related problems. Traceability, link recovery, but there's several other ones. Reuse, probably it's third in terms of volume of interest, right? Option number two, well, the first two steps are the same as before. You still need to build a corpus from some software artifacts. You still need to index them with some sort of text retrieval model. But past that point, it's not a query-based issue. Instead, you compute similarities between every document in your corpus, and then you use these similarities to define some measures and metrics that reflect properties of the corpus that this information captures. And then you use that, those measures to perform the text analysis I'm talking about. So what kind of problems we address that way? Well, anything from software categorization to refactoring, reverse engineering, bug triage, defect prediction, and so on and so forth. So let me give you some examples. By the way, feel free to interrupt me. I'm going a little bit fast, so I leave more time for discussion, but feel free to interrupt me. So how do we define a software engineering task as a text retrieval problem? First, we need to define the context of the task. Those of us who worked in the field, we know that text retrieval only gets you that far. It will not solve the problem, right? You have to use something else typically. It solves a sub-problem or a sub-task. You have to define it to see which part of the bigger task is really helped by text retrieval. You have to define your input and output. That determines your choice of corpus later on. What information need you have? As I said, typically for almost everything we do in source related to software, we need more than just text. We need structure, we need behavior, we need process information. From a researcher point of view, we need to define evaluation, right? If we want to make progress in the field, we need very well-defined evaluation criteria. And remember, we're typically solving a sub-problem of a bigger one, okay? And then you remember, I listed a dozen software engineering problems phrased as text retrieval problems. There are differences between them, right? And going back 10 years ago, I remember reading many of reviews like, how is this different than traceability, or how is this different than bug localization, right? Because at the core, every one of those papers was a text retrieval problem. So you have to make sure you specify that. Okay, then once you define your problem very clearly, this is the one I'm phrasing as a text retrieval problem, well, you have to instantiate it. Yes, sir?
So I'm finding the discussion a little generic, so I'm wondering if there can be some concrete example.
I have a concrete example.
Oh, okay.
Yes.
I'll remember all this abstractly, and then when you instantiate...
Yes, so, yeah, exactly. So I have one example of one task where every one of these steps, I explain how people do it. Yes. But it's still the steps, so, okay? Yeah. And yes, I only have one example, but then we have an hour of discussion, so I was bound to 20 minutes by the chair, so. Now it's 22 because of Sol. Okay, so... anyway, so once we define this problem and all those parameters I mentioned, well, we want to instantiate it as a text retrieval problem now. So we need to define what goes in the corpus. What's the document granularity is the question here. How do you normalize your text? Then you need to index it, and here's the question you have is which text retrieval model I'm going to use and what parameters. Then I have to issue queries, right? And the question is, where do those queries come from? How are being formulated or reformulated? Then, as I said, typically, any results will be combined with some sort of other information from software, be that static or dynamic analysis results. And of course, then you worry about how you show the results to the consumer, which is typically a programmer, okay? So here's an example, okay? The task I'm focusing on, I picked it because we worked a lot of it, but we're not the only ones, obviously, as I said. Concept location in software, it's an instance of the concept assignment problem. In the realm of software, it's essentially defined loosely as locating the implementation of a concept in the code. Okay? Now, this is just as generic. If I said do that, it's a problem. Where does the implementation start and where does it end? There are not crisp boundaries. There are oddities of a programming language. The main function, is that part of all concepts or no concept? Right? These are very tricky decisions. So you need to make those steps that I'm going to go through in a minute to instantiate this in your context, right? And there are other instances of the same problem with the concept assignment: feature location, bug localization, traceability, link recovery. And I will explain at the end what are the differences, at least some of the differences. All right, so here are the steps. You need to pick up a concept. Why do you need concept location for context? Sorry, what do you need concept location for? At least in our research, and typically in the research of vast majority of the community, is software change, right? And what's the software change? It's, you define a process for it. Typically starts with a change request. Call it anything you want. It's a change request. And it's succeeded by impact analysis. So in this context, concept location starts with a change request. That's your input. And the output is the location in the code where you will start the change. Not the entire change, not the whole implementation. That's the job of impact analysis to take care of, right? So it's very, very narrowly defined, very well. Well, what sort of other information needs we need? We obviously, here is text. Everything I'm talking about, it's about leveraging text, right? Because change request is natural language, most of them. Output is in code, location in code, though, okay? But we typically, to solve the entire problem of software change, we also need code structure, behavior, and oftentimes process information, right? But for the sake of retrieval, you do not necessarily need that. However, you want to bring them in, okay? So, how do you evaluate? What are the criteria and the methodology? As with any text retrieval problem, remember, we just phrased concept location like that. You typically use what? Precision and recall. I don't think I have to define it here in this room. And you need some sort of goal set. Now, how do we define goal sets in concept location related to software change? Well, one technique that today is popular, but is to reenact change and simulate user behavior. What does that mean? Everybody's familiar with historical reenactment, right? You know that Napoleon's army and Wellington's army were in this position at the beginning, and you know what was the end, but you don't really know exactly what happened in the middle. Who killed who at what time, right? It's the same here. We can look at historical data. We know that you got this bug request or change request, and you know when you committed the patch, what exactly changed. We don't know how you changed it, but I know the input. So we build goal sets based on that, right? We have issue description, and then we have patches. Now, one challenge is the correctness of those patches, right? Razvan, you mentioned yesterday you did bug localizations. How many bug descriptions and patches have you used? What was your data set? Right. Order of magnitude? Did you manually check all those patches?
No,
right?
Thousands.
Right, but how many of those you checked manually?
No, we just...
You see, so we have a problem. This is still a challenge in the field. There's very little curated data out there, right? So we don't know whether those patches are actually fixes to bugs or contain other commits as well, right? It's a problem. So it's very hard to do. We have very little curated data. And then you simulate the user, and this is a little bit of a problem. So a text retrieval technique will return your rank list of documents, right? In our case, we have an issue description as a query, and we get pieces of code returned as documents, right? Now, how do you evaluate here? Well, we assume in an ideal world that the user would go through that rank list one by one. Now, we all know that in reality that's not true, but all things equal, you throw two techniques at the same data and you assume that whoever ranks something higher or faster, it's better. So we do this assumption, right? Also, in the case of change, that's a proxy for effort it took you, how much code you had to look at, right? In reality, what happens, and we know there's data and studies about it, people actually do go through ranked lists, but they also follow dependencies and so on and so forth. So it's a much more complicated model of how people look at results, at code in general, regardless of what code returns it, okay? One of the common measure here, and there will be people in the room objecting to that, to measure the effectiveness of a retrieval tool in this particular context, is the rank of the first changed piece of code, okay? As I said, the reason people adopted that, and I'm one of the adopters of that, is because it's an estimation of human effort. Now, if you pick up a random paper from those several hundreds I mentioned, people will use MAP and MRR. That would be mean average precision and mean reciprocal rank. There is no consensus. Oh, hits at 1, hits at 5. There's all sorts of measures in all sorts of papers. And there are very, very few papers actually justifying why I picked that measure. Typically, the justification is, well, this other paper that was published 6 months ago used it, so I use it too, and I show my tool is better. This is something we as a community have to decide which way to go. Now, ideal way to do evaluation of concept location would be user studies. Very rare. I'm aware of, again, we started working on this in 2004. So that's 11 years by now. I'm aware of about 3 or 4 user studies in 11 years. Why they're challenging? There's always learning effect. If I have somebody change something on the code with using some tools and then second times without, there is learning effect. Every textbook on running user studies tells you that when there's a significant learning effect, you may not want to do it. It's very hard to control it. Very hard to control confounding factors, right? Experience, you name it. It's very costly, we all know that. And our community, the software engineering community, no offense to all of us, are insufficiently still educated on how to do this right. We don't know how to do it right, or perfectly rather, and as opposed to, let's say, psychologists, they do that from day one. We don't do that, and the reviewers don't. They complain all the time, you only use students, and so on and so forth, right? So we don't even have a notion of representative sample. So this is very difficult. Okay, now, that's the definition of concept location in terms of context, input, output, evaluation, information need. Now, how do we instantiate it as a text retrieval problem? What's the document? Okay, typically it's concept location in source code. So the corpus is built from the source code. That's the easy one. Second, document granularity. How many of you in this room did research related to this and used class level granularity? All right. 1, 2, 3, 4, 5, 6 hands. How many of you use method level granularity? Okay. How many of you use 5 level granularity? Okay, I rest my case. Typically, we do it opportunistically. My tools cannot parse methods, so I'll use file. That's the state of the art, right? Hundreds of papers later, right? What text retrieval method should we use for the problem? As I said, I'm putting words in everybody's mouth here, but our drive was, let's see the problems we can solve, not so much as match the best model to the best problem. To my knowledge, these are the most popular that have been used. Feel free to add to the list, those of you who list. Many of us tried several. Often many people just publish paper running on the same data, 4 of these, and concluded that this one's better. And as I said, the data was not properly curated, and so on and so forth. So we have a problem there, a challenge for sure. Query. How do we formulate query? Well, in concept location, typically it's manual, but you can use the issue report to extract information from it, or you can copy-paste it if you wish. And the typical way to reformulate query is through relevance feedback, right? Combination with additional information. This has been a lot of work on this. Typically, dependence static information, something like a dependence graph, or dynamic information, something like an execution trace, or, I forgot to add there, information from process like previous authorship and code changes, historical code changes are being added to it. How are the results presented? Typically like code signatures linked to the code. However, these issues spun off a subfield recently in this area of code summarization. It actually came out of this. What should we show to the developers as results, right? Okay. Now, differences from other instances. This is one of the issues, like what's the difference between concept location as I just described it and feature location, bug localization, and traceability link recovery? The differences are actually a little bit subtle, right? And it has to do with how you evaluate. Feature location, this is critical. Features in a software are subset of concepts. They are concepts associated with visible functionality. What does that mean? I can define a scenario to exercise that feature. Right? Think about it. If the concept I'm looking for, it's a linked list in the code, there's no execution scenarios that guarantees me executing, finding a linked list. But for features, it is. So this is a big difference, right? You can use, in this instance, execution traces, and actually it's desirable. And one of Dennis's contribution in his PhD was that once you combine execution traces with text retrieval, the results are orders of magnitudes better, right? So this is one of the major differences, not else, right? This is just a feature location is a subset of concept location. Bug localization, right? Some people mentioned here working on that bug localization. Well, this is very typical. This time you have to start from a bug report, right? And if it's automatic, that implies you use the entire bug description, right? Again, you might have execution traces or stack traces there. You might combine it with test cases in this case, or anything else that it's in the bug description, anything else around it. Past authorship, code changes, and so on and so forth. Something you don't necessarily have in like pure concept location. And of course, you can and typically do automate query formulation. Traceability link recovery, it's a little bit different. This time, the queries are fixed, right? You go from, let's say, a use case number 7 to the code. Well, use case number 7 is your query. You're not going to change it, are you? Whereas here, there is a lot of change in queries. Okay, so typically there's no query reformulation. Now, something I didn't mention before, traceability recall is, I argue, it's more important than precision. This changes the game. In concept location, I told you, you care about finding the place of change as soon as possible. That means I sacrifice recall for precision. If I got that guilty method on position 1, I don't care about recall because that's what I'm looking for. Traceability, recall is important, especially, Jane was talking about yesterday about tracing regulatory code. I want to make sure that all the places in the code where that is taken care of, I'll find, right? So this immediately leads to 2 different research strategies. You know, those of you who worked in text retrieval, you know that if you try to improve your precision, it will cost in terms of recall and vice versa. All right, so that's the example of concept location. I hope it's specific enough. And I have a shorter one about the other kind of problem. So here's, for example, again, this comes from Dennis's dissertation work 10 years ago. Oh, you're getting old. We defined a new cohesion metric using text retrieval for software, and it's inspired from discourse analysis, right? This was one of those, in other words, coherence measurement and discourse analysis, right? And you do the same. You index the source code, you pick your text retrieval model, and we compute textual similarity between every single method in the system. And then you take classes and you do some sort of averaging of those similarities to reflect cohesion, right? This is almost 10 years before the word naturalness came to scene, right? But we were thinking that there's an analogy between natural language discourse and software discourse. And if we can measure the coherence of one, we should be able to measure an equivalent notion of the other one, which in our case is cohesion. So Dennis worked at the time, like, okay, are we measuring a different type? And yes, we compared it against, like, I don't know, several dozen existing cohesion measures. Turns out that the textual cohesion, conceptual cohesion, how we called it, measures different properties of the code. So what can you do with it? Because measuring, anybody can invent a new metric. Well, as it turned out to be a better defect predictor than other cohesion metrics. But better yet, when we combine several cohesion metrics obtained using structural measures, textual measures, and dynamic where there was a case, the prediction power was significantly better, right? And later on, actually, some collaborators in Italy, they spun off and did an entire dissertation and future work on using these measures, because we also define coupling measures, to guide refactoring, automated refactoring. Okay? So, these are the two examples. Now people worked on cross-cutting issues. So, as I said, everything I just described in these two slides, people have done it over and over in at least 30 instances, 30 different problems. What's the problem? How do I index it? And so on and so forth. Now, a lot of researchers have done research on, that cross-cuts these various applications, right? So, what are the issues? Corpus building. Identifier splitting was a big research. Don is here in the room, probably the expert in the field. Synonym analysis to enhance the corpus and queries for that matter. Abbreviation expansion. Again, I'm pointing to Don. People used n-gram analysis to enhance the corpus, and term boosting. You know, if a term is a class name, it's more important than if it's a random word in some comment on method 15, right? So a lot of research went on that. I don't know, does anybody here in the room did term boosting? I know Nick Kraft and so on, but okay. I told you that selecting the right text retrieval model is still an open issue. So people looked at that. Two ways people address this. One, by just comparing them, like really run it on the same data, which one is better. Second, by actually phrasing the selection as a configuration problem. And Dennis and his students have done that, and Sonia also worked on that. And as far as I know, and Jane as well, right? With genetic algorithms and so on, right? So, yeah. Tien worked about 10 years ago, maybe, on incremental indexing, right? Nobody since. But people looked at this, right? Because as you've... I'm sorry, you see, okay?
Yeah, there were...
there are a few papers, right? It's a hard problem. So software changes, when do you reindex and how? How often and so on.
It's a hard problem. I'm not sure it differs from the problem for the web of updating web pages and that sort of thing. So I guess I don't know that problem in particular is different in software engineering.
Well, I think the questions is probably different when. What are the triggers for indexing, right? In software might be different than in web. I don't know. This is a research question that even Tien at the time, you didn't address this issue. You addressed it how to do it rather than when, right?
Yeah, just how to do it.
Exactly. When. So if I recall correctly, right? And people looked a little bit at vocabulary, right? This was even before the naturalness came about, because especially in all of these text retrieval approaches, there's this underlying assumption that the things I'm trying to retrieve will share vocabulary with the queries, right? So at some point, we actually looked at quite a bit of data to confirm that hypothesis. And at least in terms of, in one instance, buggy code, there is statistical evidence that they share more words with the bug description than the non-buggy code. Hence, reason you can use something like this. All right. Other cross-cutting research problems. Query formulation. Not that many people worked on this. As far as Sonia and a few other people, like what information you put into the query, right? Reformulation, even fewer people work, but the two approaches are based on, that are common now, are on relevance feedback and on query properties using machine learning. Results presentation, I mentioned, it spun off summarization out of it. And of course, information integration, there was research on adding structural, dynamic, and process information. But one thing we have not successfully addressed now, we know that it's good to add dependencies. We know it's good to add stack traces or execution traces and pass changes and so on and so forth. What we don't know is when and in which order, and people tried it in a variety of ways, but there's no consensus yet that how to do it properly, right? So that's still a big challenge. Finally, my last slide. These are all existing challenges. And let me explain. One, it's combination with natural language processing. IR, those of you in the field know, it's just a bag of words, so it only takes you that far, right? It cannot distinguish between actual meaning of opposite meanings, let's say, of phrases. So there's an assumption that if you combine it with more NLP, it takes you one step further. How? Open-ended. Matching the right tool and technique to the task. We don't have the answer. I don't know whether LDA is a better choice there than Lucene for concept location. The amount of data we have, well, of course, you're a fanatic of LDA. You'll say it's LDA, and he's right. We don't have the answer, really. I don't, as far as I can tell, there's not sufficient evidence to support either. Better evaluation mechanism. I told you that there's not consensus. You pick random 3 papers, they will have different measure and metrics on the same problem. Data availability, it's very little, right? Dennis has some data out there. We have some data out there. Half of it is not curated. We tend to replicate whatever the last paper did, but we never really assess the quality of the data. I think it's a major fallacy. If you get a review telling you this, you know it's from me. Some research a few years ago, Don, we did discuss having a session at Track on software engineering corpora, which might spearhead collecting data. Nothing happened. That was.
Well, I did check into it. They might be interested, but we would need to do a lot of upfront work.
Exactly. So we need some sort of community effort of some sort. It's a challenge, period, right? Tool integration. So as I said, we typically solve one part of the problem, right? In concept location, if I want to address change completely, I need to tie this in with an impact analysis tool. Very few of us, if any, is even doing that. So this is a little bit of showstopper of going into industry, an adoption showstopper. Optimization, most of the field, correct me if I'm wrong, we cared about proof of concept. As I said, what problems can be solved? Many of our solutions are not exactly optimal. Well, user studies, I brought that up before. Very little research on the human aspects here, as in how much do we learn while we navigate, right? Switching from I'm searching for text now versus I'm navigating dependencies. We don't know very little about those clues in the code. There are some people working on this information foraging theories and mapping them to software engineering activities. Definitely fits. But we're missing those. What are the scents and what are the clues that allows you to switch between strategies? Until we figure this out, any hope of doing user studies as form of evaluation, it's anywhere dwindled, right? So what is the bottleneck? A couple of people, Chris Parn and Alex Orso, had a paper at EAST earlier this year, and they showed that it doesn't really matter whether I rank the buggy class 1 or 15. The bottleneck is once you find the class is finding where the error is still. And text retrieval doesn't help you with that. So there are issues like that. Education, this is a problem. Probably everybody in software engineering faced this. We have to, our grad students are sort of self-educating in NLP and text retrieval and so on. And I see crossing on the other side around. Jennifer, now you're educating yourself on software engineering, right? So there is not a lot there. And of course, infrastructure. Most research groups here, we end up implementing, or rather re-implementing all of our tools from scratch. Does anybody here uses anybody else's tools for anything from corpus creation to indexing? Not really, very little.
I'm just going to say something here.
Sure.
With TraceLab.
This is my last slide, so that was the last word, yes.
Yeah,
TraceLab is the step
for
in the right
example,
direction.
For example, we ran our Exceed paper that we submitted this year, one of them. I was able to reuse lots of components that Dennis had produced and some other people. And I think that's exactly, so I think it's not quite as negative as you're kind of...
No. I'm saying it's still a challenge, right? So you have one success story in 15 years of research. That, in my book, that qualifies still as a challenge, right? And that's the way to go. Yes, you are, I think, going in the right direction, and we have to move that forward. No offense, I don't think that problem has been solved now, just because you managed to do it for your ICSI submission.
No, I was just giving one data.
Oh, of course.
So regarding the consensus on measures in software engineering, you're right. I think there's a lot of debate. For example, I don't like precision recalls. I don't even like AUC all that much.
I forgot to mention that one. People use it too, yeah.
So the thing is that I'm wondering why it is different in traditional information material. Is it because programmers, who are the primary targets of these tools, are different sorts of animals from ordinary humans who are using IR methods, or what's the deal?
So there are IR people in the room, so we should ask them. But here's my theory about it, unproven that is. As I said, we are solving a very small problem by as formulating it as retrieval, right? And then the success of your biggest problem, this is a small. So whereas I don't know, maybe in some other fields, the retrieval itself, you're kind of done when you found what you're looking for. With just text retrieval, that rarely happens in our case. Yeah.
Why do you call it retrieval? In information processing, it's called more like information extraction. And for information extraction, they use much more, precise instruments. They just better words. There are patterns. They just write regular expressions to find things. So maybe you could just not see it as a retrieval, but as information extraction and integration.
Right. There are two reasons I call it like that. One, because I'm poorly educated in the field, like many of us, I dare say. Again, we're missing this cross-fertilization. We are. This is a great place to start, for sure. Second, it took us, for example, a long time, and some papers discuss this. What's the difference in the software engineering context between search and retrieval? Search, and the consensus that came out, it was the search is when you know what you're looking for. Like, I'm looking for this particular class. So I can use regular expression search to look for its name, and there it is. Retrieval is when I don't know what I'm looking at, and I don't know how to describe it either properly. And developers do that every day. So it's one of those things, they recognize it when they see it, but they don't know how to describe it. Right? You're working on summarization. We also did some user studies. Sonia did having people describe code. It's a disaster. They can't. They don't. We don't. It's a skill we're not even teaching them, and oftentimes they don't have. And they cannot describe it when they wrote it. They cannot describe it where they're looking for it either. Well, I'm exaggerating, of course, but you understand what I'm highlighting.
I think it's even debatable whether people recognize it when they see it, especially in the concept location.
Yeah.
The first time that you actually see the buggy location.
Oh, no, you're
might
not going to find it. Yes.
You don't understand that is the
Yeah.
location of the.
That's what Alex told me. Alex also, it was Friday, we both gave a keynote at a workshop in Europe, and we discussed an hour about this, and that's exactly what he said. What they found in user studies was they put the class that contained the bug as first on the rank list. Developers looked at it and just moved on because they did not realize the bug is there. They eventually got back to it, but it took some steps. So I don't know if this type of retrieval or information extraction or search is different for developers than the population at large in other fields. I'm suspecting it is, but.
So, one thing I'm still not clear about is that, given like Alex Orso's user studies and all this, should we formulate the problem this way or should we formulate it differently? In other words, the problem of helping developers locate where the bugs are. What is the right formulation? Do we have the right formulation or should we look for a different formulation?
Yes.
If the problem is information retrieval, the right problem, do we need something else? Do we need like, some other formal methods or something that will tell us, okay, here's the bug and here's why? So I'm not, that's something I'm not clear on either.
That's what I'm saying. So we need to, once we define the small slice of it, and we agree that I can phrase this as a retrieval problem or information integration or search, then you need to define the other slices and put them together. And we as a field, I guess traceability is probably the one that managed to close the loop more than others to some degree. But yes, in many of these tasks, no, we did not.
So can we use this discussion to dig deeper into some problems? Like back to slide 4 or 5 where
sure, the tasks.
It said requirements and bug locality and a bunch of things like that. So kind of, it's also partly in follow-up to what Prem said about, so you've got this problem and you call it bug locality. That's a fairly well-defined software engineering problem because you're trying to, you could plant a bug and then you could see if your technique can find the bug and how closely you can get to it. And then you could say, well, so my question is specifically, how does the text retrieval help you with the problem? And then the follow-up question would be, what if I had some statistical analysis techniques, how does that help me? And then a follow-up question would be, suppose I add machine learning and I have a corpus, and then how does that improve? And then I don't know, if I add deep learning and all the other things, then do I even get more improvement? So I'm thinking for every one of these problems, suppose I'm not a software engineering researcher, maybe I'm an NL researcher or something, and I'm trying to understand how can I contribute to one of these, like requirements analysis. What is the...
Oh, it's a very generic term, obviously, but...
Yeah, like not what's the fragment that your text retrieval, the fragment of requirements analysis problems that you address with text retrieval, but what is the requirements analysis problem?
Right.
And then how can all of these techniques be brought to bear?
Yeah.
So I guess I want to encourage
we should pick. I didn't want to go define all 30 of them for the non-software engineers because it would have taken me 3 days.
Exactly. But if we had a couple of concrete examples that are really high leverage areas where we think we can make progress, then maybe we should.
Anybody who wants to... Okay, requirements entry. Jane maybe can talk more about it, but one of the problems, your students did that, was clustering requirements, right?
Yeah, in the area of requirements analysis, this is not an area that I've worked in specifically, but one of the big open areas is looking for innocuous ambiguities.
Looking for what?
Innocuous ambiguities. So in other words, in the requirements, there's sometimes conflicting requirements, and they go unnoticed, and the search for innocuous ambiguities is finding ambiguities that if you don't too soft.
Yep.
Innocuous. It's not on. Anyway, innocuous ambiguities are looking for using natural language processing techniques. Some people like Bishan Nusseibeh and Vincenzo Gervasi have worked in this area. So they've been using natural language processing methods to identify ambiguities that are going to impact the correctness of the system if you don't figure them out in advance. That's one of the big areas of application of NLP, actually, in requirements analysis. And I know my industry collaborators have previously told me one problem that they have is when they enter a new field, for example, in positive train control, they get all of these domain documents and they want to try and make sense of all of this massive data so that they can extract requirements from that. Not necessarily written perfectly, but to extract knowledge that would lead to requirements that they could specify. So I think these are two of the big open areas that could absolutely benefit from natural language analysis.
So are there some specific objectives that, like how well am I doing extracting the requirements so that I could tell if I, use some higher powered techniques, I would know that I'm doing better?
I would say, I don't know enough about the innocuous ambiguity area. Obviously, they've got their metrics, and I just am not completely up to date with that. In the other area of kind of domain analysis and extracting requirements, it's a really open area. I don't think there's that much work that's being done in it in terms of defining it as clearly as some of these other tasks that we know what we want to measure.
Well, let me give another example. NSF at Pennsylvania worked with Aravind Joshi for a while on like an FDA document that states all of the rules and regulations for infusion pumps.
Right.
And so their goal is to extract policies from the documents. And what I don't understand is how do they know if they've extracted, half of them or all of them? How do they know if they're if the specification that results, that's more formal, is accurate? How do they know if two of them contradict each other? And anyway, so if you define all the problems associated with this natural language analysis task, where you're trying to get specs from which you can produce software, then can we look at our arsenal? I mean, how do we approach the research in these areas to see how well we can do?
Yeah. I also wanted to ask you, the requirements as opposed to code is still a declarative text. So in that sense, it's more, should be more similar to text, to which is not requirements. So to me, the requirements and code are such two different classes of text, because the code describes a moving system. It's like describing a, it's a system that acts and has consequences and results which are used. And so it's a completely different type of text than requirements. So methods which could be appropriate for the requirements analysis might not at all, and not even be bad to use on code, because code is such a specific, totally unique type of text.
That's a correct, absolutely correct statement. Yes, but go on.
Vocabulary mismatch problem. It's a very well-known problem. That's exactly what it is.
And also, look, the approach is even that Bashar did. There was just straight use of an NLP technique that happened, and this text happened to be requirements documents, right?
Yeah.
But yes, the challenges come when we have to put up with oddities of the code and extracting that additional information and see how it matches the text.
But even with requirements, maybe we should just separate, like what are the particular tasks which need to be done on requirements, and then figure out what the NLP field could really bring the best to bear, whereas code is first of all, you need to describe what kind of text it is.
There's lots of declarative code, though. There's code that actually declares what it's going to do.
Right, but she meant it differently, right? So
no, but if you go look at DevOps stuff right now, they have things where you say, I have the following tasks, and they have to do the following things.
Yeah.
That's all I have to say.
But let me add something which is...
You have to do the following things. Requirements do not tell you what to do the following things. Requirements, as I understand, says it's basically functionality. This is what it takes as an input, and that's what we should be producing as a result.
It'll
How
be
you
more
do
like
it? Well,
dependency.
depending how you define requirements too. Yeah.
Let me add something, hold on, because maybe this is not obvious for the non-software engineers. These tasks, we can easily cluster them in 4 or 5 very distinct subsets of software engineering that have their own publication venues, their own conferences, their own everything. And very few of us can comfortably move between all 4. This is not just one field here. Yeah, sorry.
So I just wanted to comment about this question about what are some specific tasks that NLP might be able to help us with today or tomorrow. So I do want to mirror what Jane said on the requirements analysis. One question we've been looking at has been ambiguity in the requirements documents. So, and I've talked to this with David as well. I'm not sure how statistical NLP, I'm not saying it can't, this thing, I don't know how it would, be able to tell us when that something in a document, say a requirements document, is not, well, it's grammatically correct, it's statistically there, but it doesn't, doesn't mean what you might think that it means. So just as an example, if somebody in a requirements document put something that's not really shouldn't quite put in there, something like the system should respond as fast as possible, or the system something it should be about 6 feet long, or should take about 6 seconds. What does about mean? What is as close as possible? These kind of.
What do you mean? It's under specification?
It's vague. Okay. Yeah. So it's like a vagueness
But it's
question.
not ambiguity. It's vagueness.
Yes.
So you should.
What's that?
You should, so I don't have to do it.
Yeah, exactly. Terms like this. So, so this vagueness question. Yeah, that's absolutely right. I got my terms mixed up. But yes, so this vagueness question. I don't know. I know that it would be. It is an area that industry is interested in. Some collaborators of mine have looked at it, have been very curious about this question, but so far we haven't discovered an off-the-shelf natural language technique which will potentially.
Colin, I'm told that's actually on, but that you have to hold it much closer.
I have to hold it
Like that.
That's perfect.
Okay.
Yeah.
Anyway, I'm just throwing that on the table as a problem that is out there today that I know industry is interested in.
Could somebody give us an example of ambiguity?
It's sometimes stronger than ambiguity. You can have conflicting requirements, essentially asking you fundamentally to do opposite things sometimes.
That's not ambiguity.
I think the issue
okay.
about ambiguity, and I can't think of an example right now, but the issue is that every English sentence could be interpreted in an ambiguous way. It has multiple meanings. And the thing about the innocuous ambiguity is the meanings that actually impact the way people will interpret the requirement and therefore possibly build different systems as a result.
I have several examples.
There's probably ambiguity when you have like should. Something should behave like this. I mean, it could be like the system is, designed to be like that, or the inputs is more like a precondition where you better pass me things that make my system behave that way.
I can imagine quantifiers would be ambiguous as well, right? Like all requests are,
Yeah.
So when I said ambiguity, I really didn't mean vagueness.
Okay, I mean, ambiguity is when a term could refer to more than one thing and you don't know which thing.
Yes,
Like,
like
I
a
guess both
pronoun.
of these are
The use of a
problems,
pronoun that you don't know what it's referring to could create ambiguity.
Pronouns, determiners are often causing ambiguity when you say the class, the object should do that, which object you're talking about.
Exactly.
This is
That's
it's
a
probably
good
very
example.
common.
And I think the issue of should and could and stuff is just bad requirements writing as opposed to really, sorry, but.
We should write it in papers as well. We should.
But so I have this question, like, this seems like an interesting problem. I wonder about innocuous requirements in particular. Has there been an attempt to formalize the requirements to the point that some like theorem prover could identify that these things are innocuous? Like, I feel like most requirements are probably written in unqualified or unrestricted natural language text, right?
Yes.
But have there at least been small corpora where people have tried to write down a formal representation of what those requirements are to the point that a theorem prover or a Z3 or something like that could operate over it?
Well, now I wish I'd read those papers more carefully.
This is what happened with compiler specifications. They used to be done in natural language, and then Algol came, which was the first programming language to have
Can
the
you speak
syntax
up,
formally
please? We don't
specified.
hear.
Let's try to. If you raise your hand, I'll try to come to you.
I was saying that this problem has been solved with compiler specification in the past. Algol was the first language to have its syntax formally specified. Before that, it was done in natural language. So what Chris was saying, it's like doing the same thing now. It's possible. It's more difficult with requirement specification.
Sorry, just because I'm next to him. So I think there's been a lot of people that have advocated writing requirements in semi-structured formats or informal ways, but the reality is that just doesn't happen, and industry doesn't want, for the most part, industry doesn't want to do that. They want to write requirements in natural language text, and therefore that is, so you can tackle the problems in two ways. One, remove ambiguity by insisting on formal requirements, or facing reality and accepting that people don't write them that way and dealing with what we have, which is natural language.
Yeah, so Jane's absolutely right. There's a cultural context. If you look at modern software development, especially agile development, they prioritize talking to the customer over documentation. That's in their manifesto. It's basically this little Marxist manifesto of how we want to do software. And most people have bought into this now. Well, not most, but a lot have bought into it. So you're not going to get any kind of formalized requirements anymore.
In regulated markets, you do.
Yeah, but you'll get what users
text communication, you will.
But they're still usually natural language and not using a formal structure.
So I do know one project at SRI where they used a semantic parser to try to map a natural language specification into a formal specification. I don't know if other people know other projects, but I do know one on that just because it happens to be done. One of the persons was the wife of one of my former PhD students. But I forget the name of the system, but
they had data for this, or it was like?
I think they used some training data. They don't have a lot, not surprisingly.
But I think that is an interesting area. Like right now, we're discussing this notion of what I'll call a supervision signal as either an all or none case. Like, so for many of these requirements, we certainly won't have a formal specification. I totally believe that. But there may be ways that we can try to exploit the specifications that are available in certain projects to leverage for those projects for which we don't have formal specifications. Or we might have a looser supervision signal, like say somebody was willing to identify that these two requirements were innocuous. I've never heard that word. That's like innocuous, but without the is.
Yep.
Okay. So getting some visible traces of what the system should be able to learn may give it at least an approximate supervision signal. But I mean, I think there's a lot of research going on right now in the NLP front in how we should do meaning representation. And there are some attempts to do generalized meaning representation, like abstract meaning representation. Banks are being built up now, funded by the Linguistic Data Corporation. And they try to be application independent. There's a lot of compromises made there. I think a lot of the people in the next session will be talking about domain-specific semantics and how we can have some tasks that address those. But but I mean, I don't know, if you could find even the small corpora for which there are both natural language and formalized requirements, that might be a very useful resource to spur research.
Well, what we have, it's natural language requirements and code.
That's way tougher, right?
But that's what we have, right? That's
in the medical infusion pump, they have kind of the written specifications and formal models.
Right.
We do have that in one domain at least.
So I think one thing we should be aware of with all of this stuff, or at least the vast majority of it, is it uses what Audras Makis calls operational data. This is data that's left behind that was never intended for most of these tasks.
Yep.
This is basically mining the artifacts and results of software development, and most of it was not intentional to do any of this whatsoever. So I think that's why we're stuck in the text retrieval domain, because we're dealing with scraps, bits and pieces that are left behind, hints of the past that maybe are helpful, but it's not data that was meant for that. This is just stuff that people put into repositories, whether accidentally, automatically, because their boss told them to, or because it helped communicate. It's not necessarily for any of these tasks.
So as I was digging here, I hope I didn't drift too far away from the conversation, but there was a question about some specific cases where this might be useful, and I do apologize if the ambiguity or vagueness of, I don't quite know the exact term, but the problem is like this, and this is an actual problem that occurred at my industrial collaborator. Just one example, the software should have, or the software, it's saying what the requirement should be in the future. So the software in the future should have reduced memory usage compared to their competitor, their unnamed competitor. Well, this actually led to a question of whether they meant reduced maximum allocation space or reduced accesses to memory. So that's just an example that maybe there's a technique out there. Another example from related literature is if a bank customer maintains a minimum balance in his or her account, there is no monthly service charge. So that actually raises the question, do you mean to calculate it based on, and the regulations are not clear, do you mean to calculate it based on a per day basis, or is it an average over the month? So these kind of questions come up in requirements a lot. And
you know what we need? We need a dialogue. We need a dialogue system, a clarifier, saying what you mean by should here. You know, it's ridiculous to have shoulds in the requirements because
but they're there.
By minimum balance.
yeah, so should is a problem, but also the question of memory usage.
Yeah.
Can we say that memory usage
We must not
is
have
actually vague? Well,
we shouldn't have should.
It is actually, and so the tool that the industrial collaborator was using at the time when I walked in there actually did what you were saying, and words like should, might.
Yeah, it's like a
were just
checker.
highlighted.
It's a checker.
But that's a separate issue than.
Right. You know, there were attempts to have what they call controlled language. In certain companies, they were grammars, how you write your, like aircraft especially, because, or some kind of procedures when, for instance, you never put the if behind the verb because they push the button and then they see the if, right? So, so that is a controlled language, but it was not certain industries where like aircraft maintenance really adopted that and pretty much still use it. No, but you cannot have it for all software because it's unrealistic. So, but the question is, but still, some of the checkers which could check for certain cases, obvious cases of vagueness or underspecification or whatever you call it, innocuous ambiguity. I also never heard the word innocuous. It's actually interesting. So maybe that could be well used by the industry.
Actually, so this is a question for the software engineering people. So how many of these innocuous cases are ambiguous, but if you have kind of the domain knowledge about what's going on and you can kind of look at the pragmatics, it's actually not ambiguous?
So yeah, I think there's some ambiguity about the meaning of the word ambiguous. So I think it relates to the fact that software engineering is spans many different domains. It goes from medicine to all this stuff, and every domain has their own sorts of problems. I guess one question I have is if one might have to have access to a sufficient number of documents in a field, is it possible to identify terms that are important but are ambiguous? So in other words, just statistically, can you run over a large corpus and say, these terms are frequently used, but they're used in different ways? And so then that gives us motivation to actually go off and create an ontology, define terms precisely and create an ontology for that domain.
So yeah, there is work on a problem called sense induction in lexical semantics, where you cluster the context in which a word appears, and you can determine how, if it is ambiguous and how many senses it might have. I mean, it's a statistical technique, but there are methods for doing that. It's usually got under the title of sense induction.
How much data do you need?
It's a standard answer, the more the better. But
no, but we don't have too much data. If I give you the
again,
requirements,
you have to try it and see, but they're pretty standard techniques.
No, so supposing Saul could find a collection of all the FAA documents, right, ever written, could you go through these documents and say these terms in the analytics domain are ambiguous?
To some extent, I think the current technology might be able to do a somewhat decent job on that.
Can you take just 30 seconds and introduce yourself?
Okay. Hi, I'm Percy Liang. I'm from Stanford, and I work on natural language processing and machine learning. Since I guess, maybe just to follow up on my comment, I guess one thing that I think could be relevant is that, I mean, since we're talking about natural language in the context of code, right, I think it's useful to think about kind of this notion of grounded language where it's not just kind of a language and text understanding problem that we've been probably kind of, if you say, okay, let's use NLP techniques, probably the most NLP techniques will be trying to focus on understanding this kind of the sentence in isolation, which inevitably there's always kind of ambiguity, but perhaps by looking at what kind of actually makes sense in a given context. So for example, if you have something like, I don't know, initialize every element of this vector with a list or something, it's probably maybe a different list because that's the only thing that makes sense in the given code context. So there's actually kind of a lot of opportunities for a richer connection between the natural language understanding and actually the structure that code gives you.
So not to get off the topic too much, but I just wanted to mention, so defect prediction, for example, is one of those domains where there's actually a lot of maturity in the data sets. If you're looking for data sets and you want to play with them, defect prediction is a lot of data. You just go to openscience.us/repo. This is Tim Menzies' baby, and it's a lot of data in there from various people have generated over the years, and most of it is fairly reasonably curated. So openscience.us/repos. There's lots of stuff in there.
But
Not a lot of textual data there.
Not
So
textual
there is
data.
some,
No,
but
just
not.
because
not
you had defect
It's
prediction
growing.
up there.
It's growing.
Yeah, defect prediction up there. So.
Because defect detection is more about kind of structural things.
Not always.
No.
But I guess the question was really how do we leverage structure in the code to actually understand better, right, comments and code and vice versa. That's really the point. How do we merge semantics in the identifiers, and how do we actually also utilize structural information in code for understanding code and comments? That's really, I guess, a really interesting question because it can be tackled with statistical NLP methods.
So I just have a question, I guess, for the software engineering people that I'm trying to kind of get my head around, like what the current techniques do and what they maybe don't do that they could do. So is all of this based on just like matching of words, or is there a lot of like pattern matching as well, like saying this set of words matches to this pattern of code, even though there's like no word overlap between it? Or is it all just word overlap? I couldn't quite get that from the talk.
The short answer is if you utilize techniques, for example, like latent semantic indexing, which rely on dimensional area reduction, in that case you can pick up similar things which don't have exact words in the query. It's going to be based on coherences, latent coherences. So depending which underlying technique you use, if it's vector space, these are exact matches. If it's latent semantic indexing or some other technique which does dimensional area reduction, that you can pick up these ensembles.
So there's been some phrase level matching. I think Tian could talk about that.
Right.
So matching
And as it goes to Tian, I want to add that typically the various sources of information are combined, right? So the words are there, but then you look where exactly and how do, let's say, two methods or two classes that have shared words also relate by control or data flow. If they do, it means something. If they don't, it means something else, although they share the same number of words.
Okay.
Right?
Uh-huh.
Depends on your task.
Okay.
And sometimes in some application, for example, you you have the API in one language, you have the other API in different language. They use different terminology, and sometimes you cannot look and match it, a similar text to match it. So in this case, the mapping solution statistically is really helpful. Simple mapping IBM model could work, but the more sophisticated, I think it will get better results.
I guess this is a question about how kind of the academic work on this kind of relates to what's actually done in industry. Is it kind of many of these things are part of the standard development cycle of, I mean, there's a lot of software being written, so I guess what do they do, and which of these areas, I guess, are kind of most impactful?
So I guess you want us to rank this by industrial relevance somehow.
Well, if you can.
Put it that way.
Who wants to tackle that?
Well, I'll start. There's a bunch of them that have to do with software change. That's what developers do for a living every day, right?
I guess part of the question was, what do they do in industry? Is it similar to what's in the papers, or is it completely different?
Right. No, it's in most cases similar. These are not made-up problems.
But
they're not artificial.
In terms of maturity, right? A lot of these would be great if you could solve them, but we might not be there yet. So in terms of what's kind of come far enough that it's had an impact into industrial practice.
Yeah. So somebody mentioned, I don't remember, might have been in Tao's talk, talked about OLO, Google Code, and so on. So a lot of code search engines and repositories, when we started working on this 15 years ago, they didn't exist. Yeah. Now they're out there. So that happens. I know for a fact of many Microsoft Research, Gina Venolia's work, right? She built this sort of IR engines to query across all of their artifacts inside Microsoft. I know of a lot of companies who built their own internal search engines.
Right.
So a lot of this did go through. Yeah.
Right. So those would be cases where the information need is code. I'm looking for code that uses that keyword, and that's mature. But maybe applying it to some of these other problems, is that still more of an open challenge, or?
Almost everything here it's code, except maybe some of the requirements analysis. Let me think what else, but
anything on bug reports.
It's
a kind of weird concept.
Yeah.
Right, but it eventually gets to code, right? So you're looking at bug reports with a purpose, to fix it.
But I mean, I guess just to give an example.
No, I don't know what you meant exactly.
Well, if you look at bug deduplication. If you look at bug deduplication, trying to find similar documents, it's
right. So
not going
bug
to be
triage, right?
often.
Yeah.
Okay, if it's in bug triage.
Yeah.
And I'm going back to what Abram said before. I loved it, and I cannot emphasize it enough. We're using these techniques because the information we're trying to put together was not really meant for that. It's accidental there, almost.
But speaking of what propagates to industry, like Soldier sent me a link to the paper which is called Extending Nocuous Ambiguity Analysis for Anaphora in Natural Language Requirements, 2010. It's from UK and Ireland, and it's even extending analysis. So apparently there was already some analysis which they are extending for anaphora. So I wonder whether we talk about ambiguity, like how the state of the art is on that now, if there are papers like that in 2010.
Jane.
So I think one of the challenges we have in software engineering is understanding how we take these solutions, the very last mile. And I don't know, for those of you who were at FSC in Hong Kong last year, John Panix gave a really good talk. And one of the things he was talking about was how they'd actually try to take the full prediction code and just feed it to the programmers, to the developers. And one of the things he said, the problems that they have is even if you feed it really quickly, and it comes to the developers like a couple of hours, you know, after a couple of hours or something like that, they've already fixed that problem. So you're already running the code on kind of a changing target, and so the developers were frustrated about that. Were you at that talk by John Penix, Prem, in FSC in Hong Kong?
Yeah.
Do you remember his comment? Okay, well, attention. But anyway, I think it kind of characterizes the challenges we have in software engineering. It's not enough to just kind of deliver something that's, you know, 90% correct. This amount of imprecision and the challenges of actually putting it into the workplace make it really difficult. So I think this is an open issue for us.
But I guess you answered from another question. What are the remaining problems that can be successfully tackled with statistical NLP and other NLP techniques, which are, we still have 5 minutes to discuss that.
So one thing is just brought up by a Microsoft colleague here is you know, statistical methods, right, in general, I guess this is not meant as a criticism, but in some settings, they're great because they just tell me what to do and it's fine. But in some other settings, they give me some stuff and it's very hard to explain why they gave me that thing, you know? So, and you know, I think it's a good point that my colleague was making here is that, like, you know, if you can't explain to a programmer why you came up with that thing, you know, what are they going to do with it?
Right. So because I kind of sit between research and practice, one of my mandates is to take research and actually put it into practice, and that has proven like much more difficult than I thought it would be. One of the big challenges is putting something into practice and then developers just don't trust it. And there have been times where we have taken some, like say, bug prediction model that's super, super accurate and put it in front of developers and they don't use it. And we've actually resorted to using a much simpler model that has worse performance, but that I could explain to a developer, and then it has adoption. So it's like, we think that performance is key, right? That's the ultimate. But in fact, understandability and explainability is just as important, if not more so.
So back in the 80s, I'm one of the few people here that remember AI in the 80s. There's a whole bunch of work on explainable expert systems. There's a lot of work historically on that. And certainly more rule-based techniques are a little easier to do that, but it's not at all impossible for a statistical model to give you the most important factors that influenced its decision, right? I mean, so it's not like a statistical model can't explain itself. It certainly can to some extent. Now, it's not going to give you every factor because there's a lot of little pieces that may be added up, but it can give you the highest impact features that caused it to make some decision. That's relatively easy. Maybe a lot of the tools don't easily provide facilities for doing that, but in principle, it's pretty straightforward.
So Pandora tells you why you're listening to what you're listening to. I mean, you can.
I did work on explaining recommenders. That's an interesting subtask. Yeah.
Like one trick from the 80s that I don't remember myself, but I did read about, is you know, you could just train some kind of rule-based system on the output of the high-performing classifier, and say you just pretend to programmers when they do an
Kevin
explanation.
Knight did some of this.
Did he
stuff.
really?
Yeah.
Oh, okay. When was this? Do you remember?
In the 80s.
Okay.
Well, but sometimes it's more. So look, if you want to successfully use a defect predictor, it's not enough to tell you why the tool tells you this class has a high defect potential. It should also tell you what you should change and preferably how. This is a tool chain, right? So, and you're still there, the developer, to make decisions along the way. So typically, that's the other problem I kept emphasizing. We're solving just a subset of a bigger problem.
You know, sometimes, you know, for a programmer, you know, it may not be necessary to, you know, supposing the programmer issues a query, as in this Bing code search thing, you know, you issue a query and the thing retrieves some code. You know, it may be difficult in that particular setting to provide an explanation for why that code is retrieved, but it may be enough to provide some analogs or something, you know. The analogs may be kind of enough for the programmer to understand, you know, why this thing is being retrieved. So in addition to retrieving the specific answer, maybe sort of retrieving some high, something like a support vector, something very close to that, you know, some sort of like kernel type thing, something very close, which is similar to the answer, probabilistically similar to the answer that was retrieved, might be helpful to the programmer, even though full logical explanation is not forthcoming.
My metaphor was always that text retrieval in software, especially when you're retrieving code, will get you in the zip code. And then you need static analysis or something else to find your way inside that neighborhood. So it's the way it works.
Any other comments, questions? I think we are out of time, unfortunately. But we have very productive discussion, which is going to be summarized. So everybody will see the summary of it in the end. And should we just call a break?
Yeah, let's call a break and pick up again at 10:45. So let me introduce our next session on natural language programming and semantic parsing. And I'll welcome to the stage Ray Mooney, who will be giving the first talk in this session.
Okay, so I built this to sort of introduce semantic parsing to our software engineering folks, but maybe it's a little redundant at this time, but maybe there'll be at least a little more insight here. So like I said, this is an area I've worked on for a long time. And I've tended to define it this way: mapping a natural language sentence to a detailed representation of its complete meaning in a fully formal language. And what became a little bit of a famous little benchmark problem, I worked with a student of John Zelli and I back in the mid-90s. We put this together, and it's a pretty toy problem at this point, but it illustrates the point. And the biggest application of this stuff is database query stuff. So I asked a question in English, like, what is the smallest state by area? I get some logical form out that's actually executable. We originally did this in Prolog, but you could do it in any sort of formal query language. And then that goes to a database and you get an answer out. So this work started actually, as Charles alluded to, actually a long time ago. In the late 60s and early 70s, people tried to hand build these systems, and that went on for a long time. And I've always tried to view semantic parsing as sort of a translation between natural and formal languages. So this is a picture I made for one of our systems we developed called WAS, where machine translation looks at translating from one natural language to another. Semantic parsing, I view, looks at translating from a natural language to a formal computer language. Compiling translates one formal language into another, and then tactile generation, or it's probably more now known as surface generation within the NL generation community, maps a formal language back to a natural language. And I made this slide originally to motivate the use of a technique that we developed using synchronous grammars. I don't know how many of you know about that, because it was originally developed for compilers, right? Then it was adapted to do machine translation, and then we adapted it to do semantic parsing. And I really do view this as sort of the nice big picture of looking at all these different sorts of tasks. But like I said, people tried to hand build these mappings from natural to formal languages, starting like Bill Woods in the late 60s and early 70s. But it was always difficult. It was tried to be commercialized at the time. I always like to tell people this story real quick, that Symantec, people know what they originally did? They didn't do virus and malcode detection. They did semantic parsing. That was but they didn't make a go of it, which is why they switched their business model. So I said the way to do this is to learn. So I was the first one, I think, to really seriously look at how do we learn these things, where I just give you pairs, training pairs of natural language and formal representations. I usually call those MRs for just meaning representation. And then you have a semantic parser learning that then learns a semantic parser automatically can map language to meaning. So my real contribution to this was starting in the mid-90s to really try to focus on how do we learn these things. And since then, that's turned into a little bit of a cottage industry. And I was sort of working in isolation for many years, but then thanks to Luke Zettelmeyer and Percy Lang, who we're both happy to have here, and maybe some other folks, it's become a fairly widespread area now. Just a little bit to tell about what's been focused on lately. One is reducing supervision, so I don't have to give it full sentences and meanings. I can just give it like query answer pairs. That's something that Percy worked on, amongst others. And other types of weak supervision or even unsupervised semantic parsing. A student here at UW, Hoi-Fung Poon, who's in the NLP group with Chris, worked on unsupervised semantic parsing. Another big topic lately has been scaling this up from these toy little databases to really fairly large databases like Freebase. Again, people like Luke and Percy have done a lot of work on that. Another thing that's come up already is this idea of grounded learning. We actually connect language to perception and action. There's been a fair bit of semantic parsing work on like commands for robots. So I've done a certain amount of this, and some other people, either simulated or real robots, where you actually translate natural language into a sequence of commands for a robot. And then the most recent thing that I've gotten interested in and makes connections most to this field, and is why I'm here, is okay, well, database query is a type of program language, declarative program language, but it's very limited, and there hasn't been much work on mapping natural language to other types of programming languages other than database query. And so I did my sabbatical here last fall with Chris, and we started this nice project that he's going to talk about next on actual natural language programming for this particular task of if this then that queries for those of you, or commands for those who are familiar with that. So, okay, so that's just my really quick introduction to hopefully this session that a lot of my good friends in this area will talk more about details.
Thanks. Okay, so I'll talk about this particular application. I'm calling this language to code, and some people might take exception to the code side of it just because the code is really not that complicated. We're only looking at simple if this, then that style recipes, but I think there's a lot of linguistic complexity here and ambiguity resolution that needs to happen. So it's an interesting problem from that domain. I'm thinking about like end user programming in the context of personal agents more and more. Like, I don't know, I'm sure everybody in the room is familiar with Siri. The co-founders of Siri went on to form another startup called Viv that was intended, their goal is to try to handle questions like this, right? Like, on the way to my brother's house, I need to pick up some cheap wine that goes well with lasagna. And if you think about this, I could try to parse it and analyze it and turn it into some sort of complicated structure execution graph that might be like a SQL grammar or something under the hood, but it's a real like bit of code that we should assemble based on that language that's grounded in a number of real-world databases. This is not my graph, by the way. This is stolen directly from their Wired article. I just think this is nice motivation. So I like the area that they're going into, but unfortunately, I think we need to bootstrap our process somehow, right? Like, we can't start from nothing. We need at least some sort of supervision signal to learn from. On the other hand, so those are sort of very complex programs. On the simple end of the spectrum, there's a lot of effort these days in startups like Wit.ai that got bought out by Facebook that's focused on what I think of as single function execution, right? Like if I have a command like set the temperature to 70 degrees in my bedroom, I'd like to have that execute by changing some settings on my Nest, right? And they don't do anything more complicated than that. Wit makes it really easy for random developers to take natural language statements and turn them into JSON, basically. So some schematized representation that can then be executed over. But the focus is simply on these single statements. So one of the things that Ray and I started talking about to try to get toward natural language programming is to try to find some existing resources that would allow us to train systems. And one of the most ripe resources out there was this if this then that data site. So if you go there, people can go and author simple programs that use a number of channels. They can watch Facebook and trigger things to happen with their Internet of Things or so on, and then provide a natural language description for what's happening for each of those programs. And if you go and crawl their site, you can find like hundreds of thousands of these little programs. It's really kind of a fascinating data set exactly for that reason. Let me look at some specific instances. So people are doing things like, if there's a carbon monoxide emergency, then I can turn all the lights in my house to red, like you go to DEFCON 5 or something like that. I could track the position changes in a company. So every time I see something that happens on LinkedIn, I could add a line item to a Google Drive spreadsheet. I could grab random Wikipedia meetings. You could do all sorts of stuff, right? And these are actual recipes that I saw, as well as the natural language descriptions that were associated with them, right? So you can see this is like evidence of how messy and noisy those natural language might be, and yet we should still be able to interpret this stuff, at least to some degree, right? So that's the task that Ray and my colleague Michelle and I took upon ourselves while Ray spent some time here. As far as the website is concerned, you author your recipes using a simple web GUI. We took it upon ourselves to try to schematize it into a programming language. I kind of hate calling it a programming language because it has like one statement and a limited list of actions and so on, but it seems like a nice starting point nonetheless. And our first attempt to address this problem was to look at it like a machine translation problem, because I've been doing that for like 10 years now, and the whole world to me looks like a machine translation problem. Then we found out that the association between the text and the code was not all that strong, and so we started having to reach more towards program synthesis-based methods, and we have a paper at ACL about this from earlier this year. Oh boy, I'm running short on time. So the data was very noisy. One of the things we wanted to be able to do is see whether humans could agree on this task, so we also took a bunch of these if task descriptions and gave them to mechanical Turkers and asked the Turkers to try to reconstruct the program. And so it was very interesting. Like, we put this up on mTurk and got some very immediate responses. So people are definitely willing to do this kind of stuff. In fact, a bunch of people were excited about it and said, hey, it looks like we're trying to train a better personal agent. How can we help you more? Let's see. The accuracies are maybe... If you look at the initial accuracies, then they're not all that encouraging, but that's on all of the recipes. Many of the recipe titles are just terrible. People will type ASDF or something for their recipe title. So one of the things we did is try to subset those recipes into those that are written only in English, those that are intelligible as far as the Turkers are concerned, and those situations where Turkers agree. And it seems like under those conditions, we can get 60, 70% accuracy on this task, which means we can do some interpretation of these moderately complex programs. So I think there's a bunch of next steps here. We can look at like sort of refinement dialogues. That's one thing that I'm working on. We could try to extend the language beyond just if-then. Looking at feedback loops is really fascinating. But I think using this found data resource to help bootstrap natural language understanding is an interesting direction. Oh, there you go.
Okay. Hi, I'm Gagan Bansal. I'm a first-year PhD student at University of Washington. I'm advised by Dan Weld. And I'm going to be talking about synthesizing conditional programs from natural language. It's sort of an extension of the work that Chris and Professor Mooney have been working on. It's an incredible disadvantage to follow the experts, but I'll try my best to motivate the problem. Okay, so personal digital assistants are ubiquitous today. We all have one in our pockets right now. So I'll give you a real life example that I tried. So I went and asked Siri and Google Now, is it going to rain tomorrow? And both of them actually gave pretty good responses, gave out a table of the weather forecast of the entire week. But then I changed the query a little bit and said, notify me if it's going to rain tomorrow. And both of them gave really vague responses. Siri actually thought I was asking it to set a reminder with the title, if it's going to rain tomorrow. And Google Now just turned to web search. So clearly these assistants today are not capable of understanding these simple instructions. And the motivation is that these personal assistants, you just don't want to query them, do question answering with them. You want to be able to instruct them, learn your preferences, and do things on your behalf. So again, as Chris mentioned, there's a really simple program you want this assistant to understand at this point, which is if the Boolean rain is true, then call this notify function, and they can't even do that right now. So we've been thinking about solving this problem using dialog systems. So there's a kind of a parse, clarify, execution loop here, where the first step is given an input, you try to parse the input query, and then based upon whatever prediction it makes, a decision theoretic controller tries to decide whether to ask for a clarification from the human or whether to execute it. And this is based upon a utility model of the human and the confidence it has on the output. It could clarify about the functions and the arguments. If it executes, it can get the feedback from the human. So I just started at this point, so as a warning, I would like to say that we don't have any cool numbers to show you guys. But I would love to hear feedback on the approach we are about to follow. So as Chris mentioned, one of the ACL papers tried to do this. There are a lot of data which try to map these sentences like archive your missed calls from Android to Google Drive to the abstract syntax trees. And I won't explain the paper much, but basically one of the ways I like to view it is that it was a subset selection problem in the formal language grammar that you're trying to map to. So I've been thinking about improving their parser, and one of the ways to improve the parser is by relaxing the independence assumptions. So if you attended Daniel Dollar's talk yesterday, he talked about you can think of parsing as a sequence of steps you have to make, and you have to decide at each point how much history to condition on. So I'm basically trying to use more history to condition on, so that's one of the things. A challenge is sparsity in the data. Another way to improve parsing that we've been thinking about is using another source of alternate form of supervision. So we've been thinking of using API documentation as a source of weak or distant supervision, if you want to use that term. So if you go to IEEE.com, you can actually extract these really nice descriptions for all these functions. So for example, for any missed calls, you can get these really nice descriptions saying, this trigger fires every time you miss a phone call on an Android device. And I think a lot of you can see there are a lot of trigger words that you can use to accommodate these features in the graphical model. And the benefits of using this kind of supervision are twofold. You can not just improve the parsing, but you can automatically try to extend to new functions as soon as the developer pushes them to the API. OK, so now I'll talk about clarification. So learning from user interaction is this fascinating idea. There was a paper by Eric Horowitz called Principles of Mixed Initiative Systems, which talks more about this. But here, so for example, example clarification system could ask for the same example: notify me if it's going to rain. How do I notify you? Do you want me to send you an SMS or an email notification? So in the cases where the queries aren't specified. While we're interested in learning from user interactions in the long term, we've initially been thinking about using crowdsourcing for bootstrapping the system. And in this case, it can be actually hard to get high quality dialog logs. So we've been thinking of using more complex workflows like iterative improvement workflows, where you basically ask a question from the worker and then you improve till you have a reasonable description or the labels you have, and then you finally vote on it and get high quality data. And and you have a decision theoretic controller again to get the good workers to label the data. The benefits are again twofold: you get higher quality data, and you can also run the utility model for the users. Thank you. That's it.
Hi, I'm Yoav, and I'm going to very briefly talk about some of the work I've done on situated learning and understanding of natural language. So Ray introduced to us earlier this problem of semantic parsing, where one takes sentences and map them to logical form representation of their meaning. And this gives us this very formal representation that the system can respond to, and also very expressive representation that can capture the complexities of natural language. So within this problem, my work focused on recovering the context-dependent meaning of language, how we can use various learning signals that requires less supervision, and how we can do this all in scale. I'm not going to discuss the scaling aspect in detail today, except saying that the most work, as well as the work that I'm going to talk about today, uses relatively small and mostly very well-defined domains. And there is this really interesting challenge of how you can do broad coverage parsing. And we have a paper about this recently. So what do I mean when I talk about context? And to illustrate this, I would like to show you a very simple and short example of our algorithms on a PR2 robot. So on the top left here, you see the robot's point of view. On the right, you see me teaching the robot and use skill by using speech commands and by manipulating its arms. So this is a programming by demonstration scenario. And on the bottom left, you see the representation of what the robot is learning. And as you will notice, as I give the robot commands, I don't specify exactly what the arm or gripper I'm referring to. But the robot is able to disambiguate and understand in this case that I mean closing the left hand. And as the interaction continues, and I'll say close again, the robot will try to disambiguate. And in the next case, we'll understand that I'm closing the right hand. So what's happening here is that the robot is continuously tracking the state of the world, specifically what the agent is manipulating. And it uses this as contextual information to disambiguate the user's command. So this is a very simple example, and the language here is as simple as it gets. But I'm showing this to you because it really illustrates how jointly reasoning about the state of the world, the action to execute, both of these things are the context, and the language itself leads to much better communication. But of course, language is much more complicated, and contexts are much richer. And this is something that Ray and this is the problem that Ray also worked on before us. So in this case, we worked on interpreting instructions like place your bank against the wall of the T-intersection, turn left, and so forth, and executing them in an environment where you have a robot navigating in a maze with a lot of things that the instructions can refer to. And the challenging thing in this scenario is that you really have to take the state of the world and what the agent observes into account to be able to execute these instructions accurately. And this actually allows some very interesting interplay where the state of the world determines how the agent understands language. Language understanding determines the actions that the agent performs, and these in turn actually specify the state of the world. Okay, so the second aspect I would like to briefly talk about is the learning problem. So a big challenge here is learning with less supervision. So our goal in learning is to take sentences paired with some sort of supervision. We have this corpus of many sentences, and we like to learn this function that maps from sentences to logical forms. But the challenge is that annotating each and every decision the system has to make is extremely labor intensive and requires very specific expertise. So the first solution that people adopted is, okay, let's not annotate all the decisions the system has to make, except instead let's annotate only the final logical forms. So this really saves up a lot of the work, but it's still relatively labor intensive, and creating these logical forms requires specific expertise. So the kind of stuff, the kind of approach that we have looked at in previous work is trying to ask what kind of learning signal we can get from context. And we showed that this allows you to learn from a very easily gathered supervision, and in some cases without any annotation at all. So for example, we can look at a conversation, in this case between a system and a travel planning, between a user and a travel planning system. And something that I would like to highlight when we look at this conversation is how systems can recover after they fail in these kind of interactions. So in this kind of scenarios, the user can make requests such as from Boston on the 7th of June with American Airlines. And if you ever try to give this kind of a request to a system like Cortana, for example, I have to use a local example, then you're going to get something like, I'm sorry, Dave, I didn't get all of it. Flying to New York, what date would like to depart Boston? So the system completely missed the date and the carrier. It did get the origin. So what this system can do next, it has a specific goal, and it's interacting with the user. So it can simply start asking for questions, and using very simple questions, continue the interaction, creating a conversation that is far from ideal, but this kind of recovery will allow it to continue, but also include a lot of information about the user request that the system initially failed to understand. So what we showed is that you can take this kind of recovery, and without any notation except recording these conversations, you can learn to better understand the user request, learning from failures to avoid this kind of failures in the future. And in the long term, incorporating this kind of learning approach into a complete dialogue system will allow these kind of systems to continuously improve for interaction with users. So you have systems that start with a relatively primitive understanding of language, and by talking to users, become better and better. Okay, thank you very much.
So just press next. Okay. Okay. Hello, everyone. I'm Percy. I'm going to talk about executable natural language. This is a Python program, and it's nice because you can execute it and you can get an answer. And the way I think about natural language is very much the same way. I think about natural language as encoding some sort of computation that we want to actually be able to perform. So I'll give you two examples of some of the tasks that we've been looking at that fall under this kind of general framework. One is question answering. You're given a question, you're given a table, and you have to kind of understand the computation that's implicit in the question and identify 2004 as an answer. Here's another example which similar to what Yoav talked about. You're given a robot instructions, get the cup filled with water, and you want to map it to a sequence of actions that actually gets executed in the world. So, what I actually care about is the actual execution. But the way I'm going to solve it is via semantic parsing, where the idea is that you map natural language into logical forms. And this breaks down the process into two parts. One is the understanding and mapping the natural language to the logical form. And the second part is knowing the answer or figuring out what the actually performing the execution. And what I'm interested in doing is learning this pipeline where you actually don't see the logical forms. So perhaps this is a slightly different philosophy than some of the other talks where I only view the logical forms as intermediate representations for getting the task done. So we developed some learning algorithms. This is kind of just a toy intuition for understanding what's going on. So the learning algorithm doesn't know anything. It's going to start out with an example of a question and an answer. It's going to generate possible candidate logical forms, execute them, and see which ones actually get the answer right. Often there's kind of ambiguity, so you go to more examples, and then over time, you gradually see kind of statistics emerging, and then you might identify, the word to press means place of death. So I'll list three kind of open challenges for kind of working in this framework. The first one is the fact that we're searching over the space of programs. It's very, very large. and this could take a while to actually get. So in some sense, we're doing kind of program induction, which we know to be quite difficult. So it's really like finding a needle in a haystack, and we've developed some techniques to try to address this. The second challenge I want to mention is this what I call high-level concepts. You might think that who is Bill Gates' grandmother is a really easy question because all it really means is grandmother of Bill Gates. But actually, when you're mapping natural language to code, the primitives of the code are not often aligned with the primitives in the natural language. In particular, code generally has lower level primitives, and you need to be able to kind of induce this whole structure, gender, female, parent, parent, and realize that this means grandmother. And the third challenge is been something that kind of, I think, plagues us all, which is kind of the lack of data when you're talking about relating natural language with actual code. And the traditional way that you go about doing this is, well, you write down some examples of inputs, maybe this is ad hoc, and then you get them annotated with code, and then you can train whatever you want. So in a recent paper, we actually found a strategy that turned this story around, which was actually quite effective. So instead, what we're going to do is have a grammar that is a grammar really over programs. So we're going to generate a bunch of programs which are kind of representative of all the primitives that we're likely to see. And for each one of them, we're going to generate some half-broken English that describes the semantics, but is not really that fluent, like person that is author of the most number of articles. And then we go to crowdsourcing and ask them to paraphrase these into more realistic utterances. So you get nicer things like who has published the most articles. And as a result, you actually get a nice data set of examples of questions and their logical forms. Okay, so one thing that I guess for this audience I'm quite interested in is smarter autocomplete in contexts where you might imagine you're writing this function and you want to say, well, geez, this is Java. I don't remember how to open a file because it's Java. So I'm going to type in some keywords in natural language, and I want to be able to map this onto the code in context. So this is something that we're starting to think about more. So in summary, I think natural language is, I like to think about it as actually encoding some sort of computation that's been done. Semantic parsing is kind of our best way, I think, to actually get there right now, but I'm open to kind of other types of representations, and there's a bunch of challenges and opportunities. So I'll conclude there.
Hi, everybody. Hello. Yeah, it's working. Hi, everybody. My name is Srini, and I'm a second-year PhD student at UW. My advisors are Luke Zilmar and Alvin Chung, and I think both of them have been part of this workshop. So I am mainly interested in how can we use natural language to help users write database queries. And I think this is really important because unlike other programming languages, database queries are written by a whole bunch of people who are not computer scientists, like lawyers, scientists, and people in business. So that's why I'm interested in this task. So this particular talk is about something that I've been working on right now, which is learning to summarize code. And here I'm talking about summarizing database queries. So specifically, I'm looking at database queries which can get fairly complex like this, and I'm trying to get a natural language description of the query, which is not extremely verbose. So we don't go into every column name and table name, but this would be summarized using a sentence like this, which is like get the lowest k rows based on a formula. So this is important because this would be helpful to actually retrieve the right snippet of code. So this would actually help going from language to code. And it's also useful for commenting database queries and explaining database queries for people writing them for the first time. So since we want to learn to do this automatically, that's okay. we're using Stack Overflow as our data set, and we're using all the queries tagged with the SQL tag. And so we're using the query from the accepted answer in the post, and we're currently using the title of the Stack Overflow post as a proxy for a summary of the query. And there are about 400,000 queries right now in Stack Overflow which are actually tagged as SQL, which is very good. Currently, we're only making use of the select queries. And here's a distribution of tables, columns, functions, and subqueries in the queries that we're using. And as you can see, we do have some fairly complex queries with 2 or more subqueries, 4 to 5 functions, and many tables and columns. So, so this is entirely preliminary work. We have some baselines. One of them is an information retrieval baseline where we're finding the closest query in the training set by abstracting over the table names and column names, and using the title associated with that as a summary for the query. And we also compare with phrase-based translation using Moses. And the kind of models that we're using are these encoder-decoder LSTM models, which have recently been successfully used for MT tasks by Sutskever et al. At Google. So the way these models work is we're modeling the conditional distribution of the next word given the entire input and the words produced so far. So we treat the code as a sequence of tokens, and we generate a distributional representation of the entire input by passing it through an encoder LSTM block. And the decoder part of the model is a neural language model, which is conditioned on the representation of the input. So even with this kind of model, we have some preliminary results. We are going to do a human evaluation eventually, but right now we're just using blue scores, and we're already doing pretty well as compared to the information retrieval methods. I'm running out of time. But here are some of the predictions that we're getting right now. And some of them are fairly good, but we're still running into some issues. So we're mainly going to augment our models using 2 recent ideas. One is the idea of tree LSTMs. So since SQL is code, we have several tree representations of code, and we can generate a richer distributional representation by composing over a tree representation. And for SQL, we have the SQL parse tree and the relational algebra tree. So the other idea that we're looking into is this idea of neural attention models. So instead of compressing the entire input into one distributional representation, we keep representations of all the tokens, and in the decoding phase, we can decide which representations are more important than others. So we use the soft alignment model, which and we can also see a visual representation of whether the model is working or not, because we get this soft alignment. So here it learns that count in the output aligns with count in the input. And this is our proposed model, where we generate a distributional representation of the input code by composing over the SQL parse tree. And we use an alignment model over the entire parse tree. So the model learns to associate words in the output with nodes in the parse tree of the input. And that's all I had. Thank you.
There's no clicker. Right there. Okay. Hello, everyone. I'm Nate Cushman. I was at MIT and I will be at MSR, but I'm technically unemployed right now. So this is going to be a little repetitive because I have the disadvantage of going close to last and not having seen anyone's slides before I made mine. So forgive me for that. So my goal is to enable lay users, I guess like a lot of other people, to program or to write some form of program in natural language. Computers are part of people's everyday life, and as a result, lay users are now wanting more and more to do complex and specialized computational tasks, and many of these still require them to write some form of sort of formal program. And most of these users are not very adept at using formal languages, but they're quite adept at using natural language, and there are many existing resources written in natural language. So a traditional focus of semantic parsing, sort of, in sort of Ray's perspective of this, more so than I think a lot of the other talks you've just seen, which are much more sort of the recent work, is formal languages designed specifically for use with natural language. So these include sort of these abstract representations where they're not necessarily connected to any computational device underneath, but they're just trying to sort of generally describe all possible things that someone might say in a formal way. So this is AMR and prop bank and FrameNet. Then there's also more of this stuff that I think we've seen here, which is these logical representations for describing natural language. And these are things like knowledge-based schemas or robotic languages. But again, we're designing the schema itself or the robotic language in a way that we know that it's going to map nicely to natural language. And there's a key advantage of that, which is that we have this close structural alignment between the natural language and the formal language. So when we say, walk until we get to some point, we have some, representation in our formal language that says walk until, And the disadvantage, though, of course, is that the representation just needs some linguistic expertise. So these can't be designed by lay users. You need some either natural language processing person or some linguist to kind of come in and design these things in a way that they know it's going to map nicely to natural language. And there's very little agreement on people. Everyone is sort of coming up with new representations for new domains. And often these representations are very domain specific, but, in some sense by necessity. And as a result, there's no data in the wild. So the alternative approach that I've sort of taken, as well as a lot of the work that we just saw, is mapping natural language directly to existing programs. So this is sort of trying to take off-the-shelf programming languages or off-the-shelf systems that have an API to them already and use that as the formal representation rather than something that we manually designed to map nicely to natural language. So some examples of what I've done are take a natural language description of a text query and from that generate a regular expression that we can actually execute in order to perform that query. Or take a natural language description of some complicated math problem and generate the system of equations which can be solved in order to get the answer to that problem. Or take some description, natural language description of a virtual world and use that description to help us learn how to generate programs that will actually perform a task in that world. So why these sort of existing programs? So the main thing is that formal languages already exist for these many domains of interest. So people have gone and painstakingly written down APIs and programming languages for all sorts of things that people care about. And we can take advantage of these existing systems and APIs. And secondly, there's lots of natural language resources for these existing systems that we can also take advantage of. Documentation, help articles, and so on and so forth. So we don't have to necessarily generate this data. It's already out there in the wild. And that's, I think, the biggest advantage of working with these existing systems. And so our goal, as such, our goal here is to learn entirely from data that's either readily available or easily gathered. Sorry, I missed this last point, which is to say that even if the data is not out there already, we can take advantage of users who know how to use these systems in order to generate the data for us. So there's a bunch of challenges that come up when we are not allowed to design the language specifically to map to natural language, and I'll talk about a couple of the ones that I've tackled in the research I've done. So traditional semantic parsing techniques sort of work in this way, where they rely on this ability to decompose meaning. So here's a typical example from the geoquery domain that Ray talked about. And what you can see is that what we end up trying to do is map some chunk of the natural language to some chunk of the formal language and do this sort of alignment type model. And this is sort of the typical techniques are based on this, and they assume that something like this is possible. Otherwise, we can't actually do it correctly. And so the challenge when we're mapping to existing programming languages, and oftentimes the training data doesn't have this property because we're not allowed to design the language to ensure that that property is there.
So for example, here's a natural language description of a text query and the resulting regular expression. And if we try to find, for example, something that maps to 3-letter, the best we can do is this chunk here, which is A followed by 2 letters, which obviously doesn't represent 3-letter in general. And similarly for words and starting with A. And so the insight here is that we can pull tools from the software engineering community, which is that we can determine the semantic equality between seemingly different programs. So if the training data is not decomposable, like this example that we just saw here, then what we can do is find a semantically equivalent program which is decomposable. For example, this regular expression here, where 3-letter maps to the first chunk and words the second chunk and starting with A the third chunk. So that's the second challenge, is that even when we have existing resources, we have existing a formal language and existing natural language, we often don't have them in parallel out there in the wild. And so we need new training data of this form in each domain. And so the second insight is that we can execute some possible interpretation of the resulting natural language and learn directly from those results without any labeled training data at all. So consider the domain, the virtual world of Minecraft, which many of you may be familiar with. Here's a sentence I pulled from the Minecraft wiki. Cooked fish is obtained when raw fish is cooked in a furnace. So maybe that means that in order to get raw fish, I need to first have cooked fish, or maybe it means in order to have cooked fish, I need to first have raw fish, but I don't know which is the right interpretation of that. But if I give this first thing as a constraint to some underlying planner and then ask it to perform some task of producing raw fish, say, then it's going to fail to find that plan, find a plan correctly. And secondarily, if I give this constraint to the underlying planner in performing some task, then the planner is going to actually succeed. And we can use this signal to interpret text via some form of reinforcement learning. And finally, I just want to say going forward, I'm particularly interested in probabilistically modeling the domain using unlabeled data. So utilizing these existing huge open source repositories in order to learn to correctly interpret ambiguous or underspecified natural language by sort of filling it in with, well, what do people usually mean? You know, what does a common program do in this particular case? So that's it for me, and I guess there's one more person, right? UA is up. Okay.
May I have a web browser?
Oh, yes. Which one do you want?
So I'll start with a demo because my slides is of poor quality. I think the slides are ordered descendantly by quality. Right. So here, this is what we want to do. So we want to enable programmers to write a query in the IDEs. In this particular case, read file line by line, where you can specify the location of the file variables through a variable PTH, and we actually suggest the code where you can read the file line by line actually with the variable correctly placed in the right context. Now, this is information retrieval. See this little link here saying that it is coming from Stack Overflow. So we basically retrieve a piece of code and try to adapt it to the user's context. Now we want to do this from scratch. We want to generate the code from scratch, given the query, given a very fuzzy query. I'm not sure why we need to do this, but somehow it fascinates me. Okay. So let me switch back to the presentation here. We want to look at a problem from a statistical translation point of view, but when we're trying to do that, we realize this is a scenario of a question answering. The problem here, the challenge here is that from SMT point of view, the source and the target are roughly 1-to-1, but this is not the case for question answering. You have a large gap between what you have in the query and what you will suggest in the solution. So if you think about the SMT skeleton Bayesian equation, you have a likelihood function, and you have a prior for the language model. So in this answering case, when you happen to have the opportunity to look at all the queries that people ask through a search engine, they're crazy, and you realize that you cannot actually extract a lot of stuff from the query themselves. So you will have a fairly weak likelihood function. So in order to design those systems, you have to have a very strong prior. That's why we are focusing on the API-related queries, because APIs are very predictable. Each API type may have 5-10 kind of popular ways of writing. So, and this can be learned with various techniques that are abundant from literatures, and that's what we did. So we relax the requirement to the natural language understanding. What we want to do is just to get the API names, a couple of API names from the natural language. That's it. And what we did is that we leveraged on a search engine's click-through data. There is an R missing here. So it's click-through records where what people type in the search bar and what page they actually click on. And if we look at the web pages themselves and extract all the code there and trying to figure out what are the API names, we can build this big reference table from the phrases or the words from user queries to the API names. We actually used the simple IBM Model 1 to build this concurrence table. And for API patterns, we learned all these patterns using a vanilla mining technique. We learned those patterns from GitHub. Now, the code generation part is straightforward, meaning that we need to start from a query, figure out a couple of most likely APIs, and go to our pattern library to figure out what are the most likely patterns, and then try to combine them together. So this is the code that we generate from the query match regular expression, and this is exactly the code, no character more, no character less. Actually, it contains 2 patterns because the IBM Model 1 tells us the most likely APIs are regex and match. So these are 2 patterns woven together. One starts from the creation of a regex object and then ends at calling match here. And the second one is for match. So the match is created implicitly by the match invocation, and there is a if condition saying if the match is successful, we get actually some data from the matched part. Now, so the synthesizer actually just weave those 2 patterns together. Of course, there's something more to handle. For example, all the variable names needs to be in the right form. So these are just calculated by looking at what's the most popular variable names for this particular API operands. And all these things are done independently, so they may look weird when you look at large piece of code, but that's what we are right now. Thank you very much.
Okay, yeah, so I guess now it's just open to general discussion, either from the speakers or the general audience. Chris and I just compiled a sort of very summarized set of topics that we might discuss. A number of them came up. One I like is the dialogue. I like the idea of using these external sources of knowledge like the API manuals, the API manuals. That's really not on our list. Discourse came up where, a sort of conversation where you're not going to get it the first shot. You're going to have a discussion with the user to sort of refine the program in natural language rather than just get it the first shot. Another one I put at the end that didn't come up, but at least I know I've had discussions with Nate about this, is not just doing language alone, but combining it with sort of program synthesis from I/O tuples, input-output pairs, or by programming by demonstration. I know your regex work does this, right? It does a natural language sentence plus a couple of examples of what you want the regex to match or not match, right? So I think that's another interesting issue that didn't really come up in the talks, I think. But anyway, I think it's open. Yeah, Brian.
So somebody mentioned BLUE as a way of evaluating the result of the output, and there's been some criticism in the software engineering community about using BLUE. Because, you know,
there's plenty of criticisms using BLUE.
Because one token being wrong might be arbitrarily horrible.
Yeah.
You know, in an output program.
Yeah, everybody hates blue, even in machine
I always say
translation.
these things are like what Winston Churchill said about democracy. I assume people know this. It's the worst possible form of government except for all the others.
No, but we have exactly this problem. It's just that I haven't seen anything better out there, and it's oftentimes really expensive.
Meteor is sometimes used, but anyway.
I mean, maybe they may be epsilon better, but I don't see them being a quantum leap better. And human evaluation is often very expensive, so I think there is no substitute for human evaluation. But also, I can't emphasize enough the impact that a quick automatic evaluation metric made on the progress of the machine translation field. Because before that, we were gated by just producing results and running them by humans. And so the read, eval, print loop, like that development cycle was just so slow. Having even an imperfect automated evaluation metric made the field really take off over the past decade.
The evaluation metrics, but that's really relevant to the code to language part. I don't think anyone would propose using BLA for doing evaluation of language to code. Is anyone? I don't think.
It has been done. I mean, I'm just saying there's a couple of other automatic.
It's bad enough for natural language, but doing it for programs is, because it wasn't, that's something that even wasn't even designed for.
You could compile it, you could type check it. You know,
Yeah. Yeah, well, what Chris and I did, we tried, because our thing was so simple, it's just like if there's like a so-called channel on the if side, a channel on that, and then they have arguments, we sort of broke it down into accuracy of the different pieces because the structure was sort of fixed. But I mean, I think it is, that's why we put it on this list, is how do you really evaluate, how do you know whether, I mean, it's just the idea of program correctness in the end of the day. Is this really the right program for this natural language? And how do we, even if we have a gold standard program that someone has annotated a corpus with, now we have program equivalence, which we all know is like undecidable in the general case, right? So yeah, I mean, it's definitely an issue, is what is the right evaluation? I think we can all agree, BLA, on comparing two programs with BLA, you know, God.
Can I disagree? Real quick, because I thought about this a little bit. So there was a talk about idiomatic code, right? So I think compiling and running won't tell if it's idiomatic or not. So I'd be interested in ideas about ways to do that without using something like BLA, for example.
So, I mean, we've sort of been looking at like two levels of this. The first level is, did you get the desired answer? So, I mean, in the work that I've been doing on this and the work with Sumit and all this, there are two levels. One is, do you get the right answer? And that's sort of the first key question. If you don't get that, then it doesn't quite matter what you produce. And that's easy to check. I mean, in many cases, you had training data, you had desired output, you compile the program, you run it. If the answers match, you're great, right? Then the second is this notion of idiomatic. And I think that is a much fuzzier question where you have to sort of say, well, how close was this program to the reference gold standard? And, you know, how strictly do you want to measure that? And I don't have any deep experience with that sort of textual comparison. So.
This is what I've always done and what people in semantic parsing do. For database queries, you can compare the answer output. But that doesn't always work for all programs. I mean, there are programs that are complicated, you know, sort a list. Well, sure, you can compare for a certain set of inputs, but again, it's a program verification question at the end of the day, whether that's sorting an arbitrary list.
I mean, just to make the problem even more complicated, I think that even, you know, evaluating whether the program is the same as the correct program is not good enough, because a lot of times when you give a natural language specification, you only care about some limited set of inputs, sort of implicitly. And so actually you only care that you get the right answer on that limited set of inputs, and there's actually multiple different sort of formally, semantically different programs that are really correct in terms of what the natural language is saying, in terms of the intent of the user, rather than sort of what the gold program actually does. So.
So this is going to tie back to evaluation, but I guess one thing that seems maybe a little bit not ideal is that I guess the domain specificity when you actually kind of work with semantic parsing, you know, we have things that do database queries, we have things that control robots and regular expressions, and it seems kind of still, you know, a lot of the techniques are kind of shared, but it seems, you know, still a bit fragmented. And this is kind of in contrast with, you know, broad coverage semantic representations, which don't give you exactly you know, the precise meaning or anything executable, but at least it has kind of broad coverage. And so I guess to connect up with the software engineering, it seems like in software engineering, because you're dealing with such large code bases, you're kind of basically in the broad coverage domain, as opposed to, for example, if you're maybe more in doing PL and on like you're trying to synthesize like a 10-line program that you can actually have a spec for and verify. So I guess I'm trying to think about, you know, I see this kind of parallel between, you know, broad coverage things like AMR and, you know, narrow coverage like the semantic parsing work. And then over on the programming language side, you have broad coverage. Let's just retrieve code versus like let's synthesize or verify like a very small piece of code. And kind of we're trying to move diagonally or try to kind of connect up. And I guess relating to evaluation, it seems like when you're in the broad coverage setting, you just can't really have any sorts of precise evaluation, and it has to either be something fuzzy like blue or ultimately, I guess, blue or you know, some sort of precision recall, or ultimately, hopefully, you know, some sort of human evaluation. But I just wanted to kind of lay out that.
One thing I wonder, I assume some of our software engineering folks have no idea what this BLO thing is. I mean, it just looks at sequences of n tokens and figures out how many of them you got right, basically. So it's a very surface level evaluation. I'm just trying to be cognizant here that we don't all speak the same language.
So I'm trying to understand a difference I see between the discussion earlier today and a lot of the examples we saw here. So earlier we said like software requirements are these really open-ended natural language documents, and somehow they relate to code, but the distance is so far that we're not quite sure what we can do. But then I saw a number of examples here that kind of look more tractable. So you've got the Internet of Things, you've got your home alarm system. In general, you have some kind of an action language or an AI planning language or something like that where you can construct programs, sequences of actions. And then you have utterances and you're trying to figure out, well, is the utterance ambiguous? Well, what could they have meant? And it looks like there's a lot of hope that you could actually do a lot, really, you know, in the short run, in the next 5 years. I mean, can somebody who knows more than I do, like, comment on what you think's possible and, you know, sort of what are the limitations or?
Wax poetic on that topic. I mean, I think that, you know, my perspective on this is that I think it's all a matter of, you know, how close the alignment is and how much data you have. The more data you have, the more you can sort of learn patterns from it and make bigger leaps. And the bigger the leaps that you know have to make in terms of the difference between sort of literally what you're saying in the natural language and what you're seeing in the code. You know, and I think that, you know, there's a lot of opportunity for sort of cross-domain stuff here where we have a very small amount of data maybe in some domain, but we have a lot of data kind of across a wide variety of domains to try to learn from that, to get the amount of data we need. But I think that's sort of where we're at now, is sort of we've got this sort of little translation thing kind of working, and now we want to go up maybe one level of abstraction. And, you know, and the question, yeah.
So I wonder if, you know, if you look at the like AI planning language or whatever, and then you let it get more complex, like you allow concurrency, or you can think about data races and things like that, then suddenly your natural language has like that complexity to deal with. Is this an avenue like for Nate or anyone, you know, where
where you say, now I'm starting to understand why this is hard, and this is a problem that we need to work on.
I can say something if anyone else wants to. No, I mean, I think that a lot of, I think there's sort of two complexities, and they're not, the ones that are hard for natural language and the ones that are hard from the software side they're not always correlated. And I think that, things like, concurrency and stuff like that are things that in some sense it's like, well, let's assume you knew exactly what the human wanted. Could you make it work the way that they wanted it? Right. And so the figuring out what the human wanted is one part, and then figuring out how to make it work, that's where we hope the software engineering people come in with all of their tools to kind of do magic and make the concurrency and make it work the way I would want it to work, even though I don't understand, as the user, I don't understand all of that interaction and all of what is required in order to make it work. But you're still presenting me this interface that I, as a sort of non-concurrency understanding user, can work with. So that's sort of, in the same way that, say, a high-level programming language would do that for, or something like MapReduce does for, complex clusters or whatever. You want to provide an interface of that form and then do all the programming magic underneath. And that's separate from the question of how do I get from natural language to something that I can even work with. So I'm not clear that those two problems are exactly correlated.
So when I came here, Chris and I had a long discussion about what exactly we wanted to do, and I think it's this trade-off that Nate was talking about. You need a programming language that at least is interesting enough to be, complex enough to be interesting, but yet something we could get a lot of data for, which is why we landed on this if. They're not very complicated programs, and we could get a lot of data from it by just scraping it off the web. And so that's why we landed on doing that. But it's definite that, we can only do this for fairly, limited complexity programs with a fair bit of data at this point. And I think we could push both of those, push the learning ideas, because there's been a lot of work in the database query, like Percy's stuff and things that Luke's group has done, reducing the amount of supervision we need to do that. So decreasing the data demands on the one hand, and then increasing the complexity of what we can handle on the other. And there's lots of, ways we need to improve this in both of those dimensions, I think.
There is this kind of vision of, maybe I'm speaking loudly enough, but
so in the there's this area called end user programming, where people who use spreadsheets suddenly there are 50 million extra programmers who can make errors and need to test and all of that. And now with the Internet of Things sort of area, everything is trickling down. So you're going to just have massive numbers of people writing very small programs. Facebook users will.
At least I think Chris and I, most of us, I think in this community believe that's where we're trying to focus, is this simple little programs that end users want to write. We really think that's the sweet spot for natural language programming. We're not going to, program Boeing's control of a 747 using natural language.
But if that is actually pretty powerful.
Can we handle that? And so we're trying to push. It's like,
Sorry, Abraham first, I think.
Okay.
Can you go?
So there's this area in software engineering called model-driven software development. And to the end user, it oftentimes looks like dragging and dropping boxes and arrows. And it's used to generate usually domain-specific programs. So in a lot of cases, you might be able to amp up the at least level of the user who wants the program just by having a domain-specific kind of model that you do generate too. Now, the thing with model-driven development is you've actually dropped out a lot of the language stuff in this process. You've turned it into more of like a graph connection problem, but it feels sort of similar. But I just know that quite a few people are probably unaware of model-driven development. Thanks.
So I'm really interested to see a bullet point up there that says end user debugging. That seems really hard to me, so I wonder if the person who added it has more insight, or anyone else.
Okay, so I totally have to credit Ben Zorn for this insight. So I paid attention to some of the early work that Mark Marin here and Sumit Galwani did with trying to build programs in Excel automatically through demonstration. I think that stuff is beautiful work, but sometimes it comes up with the wrong program. Yeah. And what do we do, right? Like, I think they've done some good work in trying to surface, like, maybe what are some outlier programs, maybe naturalness has something to play here. But like, as soon as we start building a formalism, we need to represent that back to the user. We need to push back somehow. I don't know how to do this. I just know that it's gonna be a problem because like I spend way too much time debugging my programs, I can't, and I know the computer pretty well, I think.
So again, I'll wax poetic on this if no one else wants to. So I think there's two interesting ideas to follow on that, right? So first is the generation side. So let's say you say something, I generate a program, and then I sort of regenerate a canonical meaning of that in natural language, which is maybe overly verbose, but that gives you some sense, maybe a better sense of how I interpreted what you meant in a way that an end user can understand. And I think the second thing is this, input-output examples. Just sort of, it doesn't do what you want. You say, where is it not doing what you want? And you give it some example of where it's broken, and then it tries to find another. So it's sort of combining natural language with input-output examples in terms of trying to do the debugging.
Right. So the first one is like analogous to this thing where you translate to the foreign language and back.
Yeah. Just to get a feel for what is it even doing. Let's assume I'm not a programmer, so I can't understand the formal program, but I want to understand what that
Which
program is
connects
trying
it to
to
the
do.
topic of the next session, which is going the other way. And the two are clearly linked. I think we only put them in two separate sessions, so it was sort of the obvious way. But there's clear connections between going one way and the other.
There's a couple. Mark, is that okay? Mark goes first.
Yeah, so I just wanted to add in, I think in a lot of cases, you see domains where, we saw this a lot in the sort of natural language to Excel formula. Like, people know what they want to do in Excel. They have some idea of what the programming language is, but the exact syntax, the exact way they put the arguments, they just don't remember, right? And so even if you can show them a reasonable looking program, they can look at that and say, okay, yeah, I wrote this in natural language. I said sum the column, 2 where the value is Ohio. They look at the formula, it says sum, it says something about column 2, it says something about Ohio. They're confident that we interpreted their intent correctly. So even though they aren't expert programmers, they understand enough about the domain language. They understand more or less how it should work, and they can sort of verify that they're happy with that. So I think there's sort of, a lot of options there. There's the paraphrase to natural language, and of course, saying, oh, let me run some examples. Here's one that's sort of ambiguous in the programs I found, which is the right answer. There are a lot of modalities that you can use depending on the complexity of the domain, the expertise of the users. Some are more valuable than others. So I think it's really important to consider the overall user experience in these tools and not just say, oh, there's sort of a one-size-fits-all or there's an optimal, right? It's very sort of subjective across what you're trying to do, and there are several good options.
Maybe I should just interject for a second, because, sorry, this is being a little bit self-serving, but one of the things that I tried to build for an early version of, there's this flash fill functionality that Sumit, and you, did you work on?
I didn't do this. This is actually reshot. So
Okay, Sumit
I should
Reshop
correct
worked
that.
on-
That wasn't
yeah.
me. I can't take credit for
But
that.
in
I worked with it
Excel,
later.
you can have an imperfect column and you start typing correct examples of what should be in that column to the right of it, and it infers a program and prints that out. So I'd made some prototype that did exactly what Nate did, that said, here's a really templatic restatement of what that program does, and it totally got cut because everybody hated it. So I think this is a great area. There's a lot of interesting HCI challenges as much as anything else. So, yeah.
Thanks. So I just, as far as the focus on the end user, I just want to say even non-beginning programmers or non-programmers have huge problems because essentially you're dealing as a programmer with very large information spaces. APIs that are enormous and complex. Possible fixes that are enormous and complex. So and there's huge amounts of data, so you can build good priors. So in this setting, maybe in addition to helping beginners, you can also help experienced programmers. Think of it as an information retrieval.
No, that's definitely why we put that bullet up there, is there's a range. And I think most of the work is focused on end users, but I know Chris and I agree that there are other applications for more advanced programmers all along the spectrum, I think. But that's why you put this power user up there, which I guess is sort of what what you were talking about, Mark, is it's they sort of know the language, but they're not very good, right? And I think this is useful at all levels. I think most of the work is focused on end users.
Let me say one other thing. I think a lot of cases is stuff. Okay, so for those of you who have written, am I being recorded? Okay, the Excel formula language is awful, right? It's just horrible to remember. It's horrible to figure out.
This is being recorded.
Yes, okay. I'm sorry to whoever said that. Yes. and so, yeah, so we've had some, I mean, user studies where people say, you know, we showed them sort of the natural language part, and they said, well, this is, I mean, they knew how to write Excel formula, right? They spent all day in Excel, they could do this no problem. But this was just faster and easier for them than trying to sort of switch out of their, I'm analyzing this data, I want to answer a question, now I need to think about writing the Excel formula. I think regular expressions are another great example, right? I need to stop thinking about what I'm trying to do and think about the funny semantics of a regular expression. So if they can say what they want, sort of free form in natural language, they're able to stay sort of mentally connected to their task flow and avoid this task switch. And that was a great benefit for them, even if they were technically capable of doing the task, you know, on their own. So it was a little bit of an aside. Sorry.
So I think it might be useful to draw a distinction between kind of programs and program output as kind of what two things that the user might want. So in the first case, your goal is to actually produce a program, and this is useful when you kind of want to execute it over and over again, or you're not executing it now. Like, you know, if then is a good example. If you have a Excel, you know, a formula, you might want to change the data and have the same thing work. But in a lot of cases in end user programming, you have some data, you just want to clean up this data, and it's totally one-off. And there, you know, programs might be the way to do it, but also you might imagine some sort of, you know, other kind of statistical procedure that just cleans it up, and then you're done. So I guess I think there's kind of interesting trade-offs. You know, when you're, you know, forcing yourself to output a program, that means you kind of fall victim to all the kind of the rigidities of your underlying primitives. I just, you know, one example I remember, like when Facebook graph search, you know, came out, and you typed like, you know, my friends who like pizza or something. It's like maps to the set of people who had clicked like on pizza, which is not what you want. So often there's kind of it's harder to bridge the gap between your user intent and the primitives that the API supplies. Whereas if you're, for example, you know, doing this in a one-off setting, then you can actually have much more at your disposal. On the other hand, you know, the one-off thing might be kind of hard to interpret.
I mean, just to add on that, I mean, I think I actually think it's a spectrum. Because I think whenever, you know, one end of the spectrum is I'm running the program on one input, like this one database or this one one file, and I want it to work. The other end of the spectrum is I want it to work unambiguously for all possible inputs. But a more common scenario, I think, is I have some domain-specific input in mind. You know, even in the case of regular expressions, I have some certain file format in mind, and I want to write a regular expression that works on this file format, not just on one file, but on all files of this format. But it's still quite a constrained domain. So there's sort of there's a lot of this question of how to think about context in the natural language, and how much you can take that context into account, and what exactly, you know, the one end is I have exactly one context, but in the middle is I think quite common as well.
Actually, I just, from that comment, I thought of an interesting thing where you actually are given the input and have to create the program based on the input and the natural language. So.
That's what I was trying to refer to in that last poll.
Oh, okay.
So Nate's done that sort of stuff.
Okay, cool. Yeah.
Well,
So,
and Gulwani and Mark have done this.
oh, yeah. I guess you've thought about that a little bit. But like you have a thing where you have columns that are separated with tabs, or they're separated with bars or something like that, or commas. So you have a text file, and you say, I want the first column uppercased or something like that. And the first column will depend on whether it's a tab, whether the columns are separated by tabs, separated by commas, separated by whatever. So, yeah.
You're saying that the distribution of the input data actually affects the program.
Affects the program itself.
Yeah.
I mean, and there's this whole area about programming by demonstration, right, that I put up there that I don't know if I've seen so much working on integrating natural language instruction with that. I guess Percy was, who was, Yoav was talking something about that, like with the robot.
Daniel Gildia had one paper on that at AAA.
And I don't know. But yeah, I mean, I think we're all agreeing that just the natural language by itself is probably not going to be, at least one-off, is not going to be sufficient. You need to talk to the user and say, what did you mean by this? You need to have a dialogue. Maybe you put in some IO tuples. Maybe they demonstrate exactly the process they want to happen on a toy example. I think there's a lot of different ways of providing input to help you disambiguate. Because like Chris said with this if, there's a lot of these things that are very short. You know, you saw he put some of the examples. There's no way you can get the whole program out of that little short little description that the person wrote. You're going to have to engage in some other interaction with the user to clarify their intent. And
So there's a question for the software engineering community. When you have specifications or programs, do you often have input examples as well, or is that just not part of the process? When you have any kind of sort of natural language resources that you're working with, are input examples common, or is that something that you would then have to go hand generate specifically for this purpose?
Well, if you do the agile test-driven development, for example, you will have very concrete test cases developed before you write code. So in that case, the input will be available.
So one thing, because I deal with a lot of the users being as we actually build systems for end users at IBM. So, and I'll wait till I get the mic here. Thanks, Chris.
So we can go through and we can build test cases and everything like that, and we do. And one of the challenges is, and then we build those initially with developers, and then when we're talking about NLP systems that we actually go and redeploy, we build those by crowdsourcing them, typically starting the company and then with family and friends about the interactions. And then inevitably, the first day that we go through and switch these systems live, like the users are just talking a completely different language. Like inevitably, it's no matter how much we think we know what we're doing, it's not there. So it's a huge problem because the people building the system and the people speccing out the system are not the end user of the system, and the end users are crazy. This isn't being recorded, is it? Sorry.
I see why they have two mic runners.
So this is something related to that, and also more from the software engineering perspective. I think the closest work in our field that deals with this has to do with code example search and system search. I mean, software system search. So we're not like building the programs from scratch, but we're finding examples that are out there. And sometimes the people that search for these are end users that don't necessarily know how to program very well, and they're looking for something that already does the job for them. And also there's some work on like searching for code examples and searching for functions that are based on input-output pairs. So you don't write a query in natural language, but you give an input and an output. So but you need to give enough examples of that to be able to determine what would be a function that would be able to give you that output. Now, I think that maybe a combination of like a specification in natural language and input-output examples would be maybe a better way to narrow down the search and find something that's really useful for the user. And I'm wondering, like, maybe even a combination of, getting programs from scratch, or like generating the programs and searching for code examples. Maybe that would be something to look into, like an intersection of the work that's been done in the two fields.
So yeah, I mean, so one of the baselines, I think it was on your chart that Chris and I did, was just code retrieval. We basically just retrieved the closest program we thought from the database. And actually doesn't do too bad, right, Chris? It's a non-trivial baseline to beat. The other thing I was just thinking on this providing examples, rather than just the user providing them, I've done a lot of work on active learning. I think it would be interesting, you understand the natural language, and then you ask the user, hey, did you want this output for this input? And you could construct good input-output pairs to ask the user to query to help you disambiguate their intent. I hadn't actually thought of that twist on it, but I think that would be a very interesting twist. I assume people who've worked on this sort of thing would have, yeah, Nate's nodding his head.
I guess maybe I could open a question about sort of intermediate representations versus final representations. Like one thing for us who've been working in NL for a while, it's kind of attractive to have an output that's a concrete, usable output that means something to somebody, you know, as opposed to something intrinsic that we designed because we thought it might be useful. Or maybe that's just my own bias. I should be careful about putting words in the mouth of other people. But on like, so for instance, mapping directly, like Nate is talking about mapping directly from language to executable code. Like I'm really sympathetic to that because we know we're solving an end problem. We're not solving some intermediate problem that may or may not have an impact on the final solution. But it feels like that's oftentimes really, really difficult. And so talking about like formal specifications and requirements, having some representation language for those that was reusable that we could map to. I mean, being able to reify some of these concepts into real languages that people might construct and that we could build, that could be cool, except we need to agree on it and build consensus. So we're actually building a reusable resource as opposed to like lots of little one-off islands. I don't know, are there any thoughts about this? I see Luke raising his hand.
I should have been a little slower because you kind of said a lot of what I wanted to say in the second half. I raised my hand too quickly. But, you know, having done a lot of this sort of semantic parsing kind of work in my research, you know, I really enjoy it. It's really great. You can build really cool systems, but it's, you know, incredibly frustrating. I think Percy or somebody else said this earlier, that you basically have to relearn from scratch for each new thing you want to do, right? And so this is one place where this shows up. So if you want to, you know, build some very custom representation for this particular task, then you just are going to have to gather data and you're going to have to relearn from scratch. And, you know, one open challenge is general purpose semantic tools. So, you know, all the people building ontologies in this room, I would love to give them an NLP thing, call it a parser, call it a semantic analyzer or whatever, that would take any text as input and provide them something useful. It's not going to solve the whole problem, but they're going to be much better off than if they just started writing regular expressions over part of speech. I don't know what that thing should look like, but, you know, there's not a huge amount of work at that more semantic level in NLP on this, and I think there really needs to be a lot more.
I beat you by a few seconds.
It's like the Jeopardy.
Okay, so I think I wanted to make a couple statements on this from sort of like a very PL perspective. Like, I don't care about what intermediate language you learn to as long as it has formal semantics, because then I can cross-compile to any programming language or runtime or whatever you like, right? I mean, that's a solved, simple problem. So from that standpoint, having a custom intermediate language that makes the learning simpler, that seems like a better place to sort of optimize the complexity gap than the actual target language. That said, I'm very sympathetic to this idea of, and we see this in program synthesis as well. You know, there's a string synthesizer or something else, all these small languages, and the problem is you have all these islands where you can do individual tasks, but really somebody wants to do some larger task. So this is where I think it's very interesting to start asking, and this goes back to sort of the compositional nature of semantic parsing, right? I want to learn something that talks about how I combine logical predicates, and I want to map to that. Then I want to be able to, you know, take that part of a sentence in isolation, translate it to a larger predicate. Now that predicate could be part of a database query, it could be part of an if-then-that query, but I should be able to translate this predicate in isolation. And then I should be able to substitute it into this larger system that knows about, you know, if-then responses. Or I should be able to substitute it into something that knows about database queries. Or I should be able to substitute it into something that knows about airline queries. So I think there's a real question of, can I do this translation on individual domains of interest and then have some sort of generalized API? So you can imagine COM, right? This is a way for arbitrary software components that know nothing about the semantics or the natural language of another component to communicate uniformly, right? Is there some sort of interface you can build that allows you to say, I have a domain that knows about strings. I have a domain that knows about conditionals. I have a domain that knows about travel. I have a domain that knows about places and restaurant recommendations. I don't need to cross-train on any of these domains, yet they can all communicate across key parts of their information so that they can be composed uniformly, even though they're all internally speaking different languages. I mean, I think that's a sort of an open, interesting question that I have that I wanted to understand more, and I don't have any good answers to, but that's sort of an alternative to this, is there an Uber language that everybody uses problem? So with that, I'll do it.
So just as far as an application of semantic parsing, I don't think this was mentioned. So earlier on, there was a debate about like the uses of languages like Eiffel and how if programmers would adopt the virtue of putting in assertions and specifications in their code, you know, everything would be so much better. We could verify programs, we could have better testing and whatever. So maybe this is another application for semantic parsing, is that if there's a way to, programmers could more naturally specify assertions, and there could be semantic parsers which would sort of insert that assertion into the code, just make it easy for programmers to write assertions. So it would be, maybe they'd give you more assertions if that was made more convenient. Just another possible application for semantic parsing.
We're running tight on time. I know Jong Dong was going to ask a question.
Yeah, just a very quick comment to what Mark said, right? There's this language, Wolfram's language, I think has positioned to be the universal language, right? It has a lot of knowledges about various domains, right? So I think there's a 7 minutes video that he has.
Boy. So Martin and then Percy, and then maybe we'll cut it off.
Very small thing. It's related to what Prem has just said. We've done non-empirical studies a couple of years ago of contracts in API documentation, and we extracted I don't remember exactly, but more than 500 or maybe 1,000 contracts in natural language in the API doc, and I guess that most of them have their counterparts in the code as guards at the beginning of the method body or something like this. So I think this might be an interesting data set to learn the relation between the contract in the API doc and the precondition in the code itself. So
add it to the dataset website.
Okay. So, I have the code, I have and I have the contracts.
Are you going to tie it together for us, Percy?
I'm going to tie some subset of things together. So I want to go back to, I guess, maybe you and Luke's comment about I guess, the need for some sort of general kind of representation. I think there's actually two types of representation. There's on the natural language side, there's basically representations like AMR, for example, that can really tell you kind of the sentence structure and what arguments go to what functions. But then, as we've seen, there's actually a kind of a big disconnect between the natural language and the target domain. Not because you're actually being maybe domain specific, but just because of the way natural language and the structure of natural language and formal languages are. So I wonder on the formal languages side, it seems like independent of natural language, maybe there should be some sort of unifying principle. And I guess maybe the closest thing I can think about is having some sort of declarative, I don't want to say data log or sort of, I don't know, a SQL. Maybe this reflects my kind of database query biases, but for example, think about regular expressions, right? A lot of the things you can actually represent and logically as well. Words that contain contains just kind of a binary predicate between a string and a string, and so maybe you can actually have representations that, just from a pure programming language point of view, that works on just kind of relations and objects, which then gets compiled down into whatever the target language is. I think this maybe becomes trickier when you have maybe things which are not so declarative. So, I don't know if people have any comments on the programming side, if there's any kind of things that can tie all the different domains together.
I think our time at the workshop is a zero-sum game. So I think answers to Percy's questions, we'll have to do that during the closing session, because we should get lunch. We were going to get started for the next session at 1:15, so that means we have just shy of an hour. I was going to try to take you all to the same place that we went to yesterday, so we should get moving, I think. So thanks to all the speakers and to everybody for a really great discussion.